Welcome to Full Stack Integration, part of the Microsoft Full Stack Developer Professional Certificate. This course bridges the gap between front-end and back-end development, equipping you with the skills to connect components, consume APIs in Blazor, and master state management techniques. You'll also learn to leverage Microsoft Copilot to integrate, debug, and optimize full-stack projects seamlessly. By the end, you'll have the confidence to build fully integrated, responsive applications. Let's begin. We'll begin by exploring the fundamentals of full stack development, diving into its architecture and components. You'll learn how to set up a full stack development environment, create RESTful APIs, and integrate them with front-end applications. By examining real-world scenarios, you'll gain a solid foundation for connecting front-end and back-end systems seamlessly. Next, we'll focus on how to interact with APIs in Blazor applications. From making and handling API calls to understanding asynchronous programming, this module will equip you with the skills to manage data flow effectively. We'll also cover best practices for integrating APIs, ensuring your applications are robust and efficient. Then we will explore state management and communication between the client and server. You'll examine techniques for managing state on both sides and discover real-time communication strategies to keep applications responsive. Best practices will guide you in building scalable and maintainable full-stack systems. Finally, we'll harness the power of Microsoft Copilot to simplify full-stack integration. You'll use Copilot to write, debug, and optimize integration code, including creating JSON structures for APIs. By the end of this module, you'll complete a comprehensive project that demonstrates seamless front-end and back-end integration using AI tools. By the end of this course, you'll be equipped with the skills to build fully integrated, responsive applications. From understanding full-stack architecture and mastering API integration in Blazor, to managing state effectively and leveraging Microsoft Copilot for seamless debugging and optimization. This journey will transform your approach to development. Get ready to connect, create, and innovate. Let's get started with full stack integration. My name is Paul Party, and I'm your instructor for this course. I've been programming computers since I was in my teens. I love programming because it's like solving puzzles while designing and creating something amazing. My graduate degree is in philosophy, where I learned how to become a better thinker. When I program computers, I can apply many of the logic skills I learned in philosophy. Computer programming not only enables you to build cool software, but I believe it can help make you a better thinker. I started my software development career at Microsoft when the internet was just getting started, and I participated in the internet revolution firsthand. I managed software engineering teams that worked on desktop and web-based software. The internet gave software developers, particularly those working on user interface, incredible new opportunities. From mobile interfaces to websites, software developers are not only creating software that's functional, but also works of art. In my career, I managed and worked with teams at both Microsoft and PayPal that focused on customer-facing interfaces and learned how to make them great. I also spent part of my 20 years at Microsoft in training organizations where I learned how to communicate challenging ideas to new learners. I also was fortunate enough to have spent 15 years teaching non-majors philosophy at a university in Seattle. This reinforced my ability to teach learners difficult concepts using ideas they can relate to. There's nothing more satisfying than to witness a learner having an aha moment where they understand something new. I'm really excited about this program. I believe Microsoft has some of the most powerful and exciting software development tools available, and I can't wait for you to learn about them. I'm confident you'll have many of the aha moments as you gain new skills and reinforce existing ones. The learning experience in this course is designed to give you a comprehensive understanding of key concepts through various learning methods. You'll be guided through interactive, engaging materials that help you build practical and theoretical knowledge. Whether you're interested in front-end, back-end, or full-stack development, this program has the tools to support your growth every step of the way. Throughout the course, you'll be introduced to core concepts and key ideas in videos. These videos are designed to help you understand definitions, processes, and essential steps clearly and concisely. You'll get to absorb foundational knowledge, setting the stage for deeper exploration as you move forward. And when you need step-by-step guidance, screencasts will provide you with a detailed practical view. These screencasts will show you exactly what's on the screen and how to work through specific coding tasks. The course also includes readings that reinforce the key ideas presented in the videos. These readings are more than just supplementary material, they're job aids. You can print them out and use them as a reference while working on assignments or activities, helping to apply what you've learned in real-world situations more easily. Small activities are included to help you check your understanding of key ideas. These activities provide quick, interactive opportunities to practice what you've just learned. After completing each activity, you can compare your work with a fully explained example and answer key. This ensures that you always know if your answer is correct. Practical experience doing tasks you would in a job within this field is essential, and that's where guided labs come in. These labs take you through the implementation of different concepts step by step. As you work, you'll receive feedback and helpful hints, ensuring you can get the help you need when you need it. It's the perfect opportunity to practice in a controlled environment while learning by doing. After completing the guided labs, you'll move on to independent projects, or you try it. This is where you'll put your skills to the test, applying what you've learned in the labs. You'll work through real-world problems, cementing your understanding of the course material. The course will culminate in a practical project leveraging Microsoft Copilot that you can use as a portfolio artifact when you begin your job search in this field. As you progress through the program, the portfolio pieces will become stronger and better representations of the authentic experience you've gained. They'll showcase your understanding of code and the ability to implement different concepts from the developer program. This course guides you step by step from understanding concepts through videos and readings to apply them in activities, screencasts, and labs. Each part of the course builds on the last, helping you gain knowledge and authentic experience. By the end, you'll have completed real projects that not only showcase your skills, but can also be included in your portfolio as you start your career. Everything you do here will prepare you for success as a developer. Let's get started.
Throughout this course, you'll complete several guided labs. These labs are meant to give you an opportunity to practice your newly learned skills in an environment where you can get help and feedback as you complete coding challenges. This video will describe how to complete the guided labs in this course. We will explore a guided lab together so that you'll know what to expect when you come to one later in the course. First, let's check the content leading up to a guided lab. This structured content ensures that you have exactly the skills you need to complete the task. In this instance, there is a practical application video that describes in detail how this concept is used in real-world situations. Following this practical application video, you can review a reading that explains the concept in detail so you can go through this content at your own pace. Next, you'll find a video that works through the guided lab itself. This video won't give you all the answers to the guided lab, but it will provide an overview of the upcoming questions and challenges. Lastly, we come to the guided lab itself. The guided lab is a simulated code environment where you can experiment with code and receive hints and feedback in a realistic coding situation. To start, I'll click Start. In this lab, step 1 is an introduction to if-else statements, so I'll click Begin. Below the simulated code environment, I can find the specific instructions for this lab. Declare the variable age as type int. Place your cursor into line 2, type your answer, and select Enter to check your work. Alright, I think I know this one. I'm going to type in INT and hit Enter. Great, I got that correct, and I got a bit of feedback about my correct answer. To move on, I click Continue. And these instructions say, prompt the user to enter their age, place your cursor into line 4, type your answer, and select Enter to check your work. This one is a little trickier. Let me try type your age. Got it. This feedback for my wrong answer points me in the right direction. Let's try that again. I'm going to erase what I had here and then enter your age. Perfect. I'll click continue. Let's try one more. Convert the input to an integer using int.parse and store it in the age variable. Place your cursor into line 6, type your answer, and select enter to check your work. I'm not totally sure here, so I'm going to click on hint and get some help. And the hint says use console.readline and then an open and close parentheses, display a message asking their user for their age. Great, that helps. I'm going to click continue and type in console.readline. And I've got it. That's how you work through a guided lab. Some questions will require more complex code to complete, so make sure you're using the hint function when you need it and reviewing the feedback provided for your right and wrong answers. Have fun completing these coding challenges that put your new skills to work.
In today's rapidly evolving tech landscape, artificial intelligence plays a key role in making development more efficient and intelligent. That's where Microsoft Copilot comes in. Microsoft Copilot is a powerful AI-driven tool that can assist developers in writing, optimizing, and debugging code. In this course, you'll leverage Copilot as a thought partner and a code-generating assistant, helping you solve problems, generate code snippets, and enhance your projects. The goal is to provide you with hands-on experience using a tool that real-world developers use to improve their workflow. In the last module of this course, you'll engage in videos, screencasts, guided labs, and independent projects that integrate Copilot. These labs will take you through how to use specific prompts to generate code, optimize solutions, and solve problems. You'll be shown step-by-step how to leverage Copilot's capabilities to strategically approach the final project. During the guided labs, you'll get hands-on experience working with Copilot. These labs are structured to show you how to craft effective prompts and work with Copilot's code generation features. You'll use it to assist in writing code, refining your solutions, and debugging. This practice will prepare you for the independent work you'll do in the final project. After the videos, screencasts, or guided labs, you'll move on to independent activities where you'll take control. Here you'll use Copilot to assist with various aspects of the project. You'll be making strategic decisions, but Copilot will support you by generating code, suggesting optimizations, and helping you troubleshoot. This prepares you to work more independently while still having the power of AI to assist. The final project will combine everything you've learned in the course, and you'll have Copilot as a key tool in your development toolkit. You'll use Copilot to help you generate and refine code as you combine the concepts from earlier lessons. The project is a portfolio-ready artifact showcasing your coding skills and your ability to leverage AI in modern development workflows. To succeed in the final module, actively engage with the guided labs and practice using Microsoft Copilot effectively. The videos and prompts will take you through Copilot and equip you to apply it strategically and independently. By the end of the course, you'll be fully prepared to complete the final project and demonstrate your skills using traditional coding and AI-assisted workflows. Welcome to the course. In this video, we will discuss how you can make the most of each part of the course to set yourself up for success. Whether you watch the videos, complete activities, or work through hands-on labs, each element has been designed to help you master the skills you need to become a confident and capable developer. The first step in every lesson is the videos. You'll be introduced to new concepts, definitions, and key ideas. Watch these carefully and take notes on the important points. The videos provide the foundational knowledge you'll need to build on, so don't skip them. They'll give you the context to understand everything that comes next. After each video, complete the readings. These readings reinforce the key ideas you've just learned and can serve as job aids. I recommend printing out the readings or saving them for quick reference. They'll be extremely helpful when completing activities, working on projects, or just needing a refresher. They're not just supplementary. They help you apply what you've learned to real-world tasks. Throughout the course, you'll find small but impactful activities. These quick exercises allow you to check your understanding of key ideas. Don't rush through them. Take the time to work through these activities thoughtfully. After each, compare answers with the answer key to check how well you understand the material. This is your chance to practice without pressure. At the end of each lesson, you'll encounter practice quizzes. These quizzes are a great way to ensure you fully grasp the concepts from the videos and the readings. Use these as a checkpoint to assess how well you retain the information. If you find yourself struggling, review the videos and readings again. The goal is to build confidence and solidify your understanding before moving forward. When you need to see the material in action, screencasts guide you. These videos show you exactly how to work through certain tasks step by step. If you ever feel stuck or unsure about applying a concept, watch the screencasts and follow along. This hands-on guidance is invaluable for understanding how the code works in real time and applying what you've learned. At the end of each module, there will be graded quizzes. These are an important part of your success as they allow you to demonstrate mastery of the material. These quizzes build on the practice quizzes, and they're a great way to ensure you're ready to move on to more advanced concepts. Treat these quizzes as milestones. Passing them means you're fully prepared for the next challenge. The guided labs are where you'll take the concepts from the lessons and apply them in a controlled, hands-on environment. These labs will take you step by step through tasks, including helpful feedback and hints. The more effort you put into the labs, the more you'll get out of them. It's all about learning by doing, so take your time and ensure you understand each step before moving on. After you've completed the guided labs, it's time to test your skills with independent projects or U-try-its. This is where you'll apply everything you've learned without step-by-step instructions. These projects are a great way to gauge how far you've come and to put your knowledge to the test. Don't worry if you feel challenged, that's part of the learning process. By completing these projects, you'll reinforce your skills and build confidence. Finally, at the end of the course, you'll complete a culminating hands-on project that you can use as a portfolio artifact. This project will showcase the skills you've gained throughout the course and give you something tangible to present to potential employers. As you progress through the program, these portfolio pieces will become stronger representations of your hands-on experience and understanding of key concepts. Success in this course comes down to using all the tools available. Watch the videos carefully, engage with the readings, complete the activities and quizzes thoughtfully, and take full advantage of the screencasts, labs, and projects. Each element of this course is designed to help you master the material step by step. By the end, you'll have a solid understanding of the concepts and real projects to prove your skills. Remember to persist, take your time, and you'll be ready for a successful career in development. To bring together all that you've learned in this course, you'll complete a project that will put your full stack development skills to work. By the end of this project, you'll have built an inventory hub, a complete and optimized full stack application designed to manage inventory data while showcasing your expertise in front-end and back-end integration. Whether you're building this project to enhance your portfolio, solidify your technical expertise, or simply create something impactful, this is your opportunity to shine. And the best part, you won't be doing it alone. Microsoft Copilot will be your trusted companion, helping you generate, debug, and optimize your code throughout the process. In this video, we'll outline the end-of-course project. By the time you complete this project, you'll have developed a fully functional and high-performing inventory management system. Using Blazor for the front end and a minimal API for the back end, you'll create seamless communication between the two, handle integration issues, structure API responses, and optimize the entire application for performance. Copilot will assist you every step of the way, ensuring your workflow is efficient and your code is robust. Whether you're new to full-stack development or have some experience, this project is designed to be approachable while helping you develop critical integration skills. Let's explore the details. The goal of this project is to build the Inventory Hub application, which will include the following components. Integration code. This establishes communication between the Blazor front end and the minimal API backend. Debugging. Identifying and resolving issues such as incorrect API routes, CORS errors, and malformed JSON responses. Structured API responses. This ensures the API returns well-structured JSON data, including nested objects for more detailed responses. Performance optimization. This is where you'll refactor and streamline your code to reduce redundancy, enhance efficiency, and minimize server load. Throughout the project, Microsoft Copilot will assist you with generating and refining integration code for effective front-end and back-end communication, debugging errors and resolving integration challenges, structuring API responses with best practices in mind, and optimizing your application for better performance and usability. This project is divided into 4 structured activities. Activity 1. Use Copilot to generate and refine integration code, ensuring the front end can fetch and display data from the back end. Activity 2. Debug and resolve integration issues, such as API routing errors and CORS restrictions, while implementing error handling for JSON deserialization. Activity 3. Implement well-structured JSON responses in the backend to support detailed and nested data for the front end. Activity 4. Consolidate and optimize your code for performance, reducing redundant API calls and implementing caching strategies. Each activity builds on the previous one, ensuring a comprehensive learning experience. Copilot will guide you along the way, offering real-time suggestions and improvements to streamline your development process. Following detailed step-by-step instructions, you'll complete a polished and optimized Inventory Hub application that is ready to showcase in your portfolio. This project will highlight your ability to develop a full-stack application and leverage AI tools like Microsoft Copilot to enhance efficiency. This end-of-course project is a great opportunity to bring your skills to life and demonstrate your capabilities as a developer. It's designed to be challenging and rewarding, leaving you with a professional-grade application and a concrete example of what you've learned in this course. Welcome to Connecting Front-End and Back-End Components, an essential part of the full-stack integration course. In this module, you'll learn how to connect the pieces of a full-stack application, from setting up a development environment to integrating front-end and back-end components. You'll explore building and consuming RESTful APIs while applying real-world scenarios to solidify your skills. Get ready to bridge the gap and create seamless full-stack solutions. We will begin by exploring the architecture of full-stack development and understanding the critical role it plays in creating modern applications. We'll break down how the front-end, back-end, and database works together, and why mastering this architecture is essential for building cohesive and user-friendly applications. This foundational knowledge will help you see the big picture of full-stack workflows and prepare you for the technical details ahead. Next, we will examine the steps for setting up a robust full-stack development environment. You will learn how to configure essential tools and manage dependencies to ensure a smooth workflow. This lesson highlights why a properly configured environment is crucial for minimizing errors and maximizing productivity as you build full-stack applications. Then we will build an understanding of how to build RESTful APIs that enable seamless communication between front-end and back-end components. We'll also focus on designing efficient, secure, and scalable APIs, and discuss their role in handling data and powering dynamic applications. This knowledge will give you the skills needed to connect your front-end and back-end systems effectively. After understanding how to create APIs, we'll turn our attention to integrating them into front-end applications. This lesson will guide you through making API calls, handling responses, and displaying data dynamically. By mastering these processes, you'll learn to build front-end applications that provide users with real-time data-driven functionality. Finally, we'll tie everything together by examining real-world examples of full-stack integration. From popular e-commerce platforms to social media applications, we'll analyze how front-end and back-end components are seamlessly combined to deliver exceptional user experiences. These case studies will inspire you to apply your skills in practical, impactful ways. As we conclude this introduction to connecting front-end and back-end components, you can see how vital full-stack integration is for creating modern, user-friendly applications. By gaining an understanding of full-stack architecture, configuring your development environment, building and integrating APIs, and analyzing real-world examples, you'll gain the skills to seamlessly connect every layer of an application. Get ready to bridge the gap between front-end and back-end systems as you take a big step towards becoming a confident, full-stack developer. Building a complete application is like assembling a puzzle where each piece, front-end, back-end, database, APIs, and version control, fits together seamlessly. Understanding these component roles is the foundation for creating efficient, real-world systems. In this video, we'll identify the components of full-stack development and their roles within an application. Let's begin by exploring the key components of full-stack development, starting with the front end, which is a key component of the application that users experience. The front end is the part of an application users interact with. It includes everything you view, click, or touch, like buttons, text, images, animations, and layouts. The front end is built using technology like Blazor, which allows for rich, interactive web applications written in C#. For example, selecting Sign Up on a form instantly displays a success message. While the front end handles interactions, it relies on the back end to process data and handle functionality. The back end is the server-side logic that handles data processing and APIs. In Blazor applications, the back end uses technology like .NET Minimal APIs to handle data processing and define endpoints for the front end to consume. When a user logs into an application, for example, the backend verifies their username and password using information stored in a database. Minimal APIs in .NET simplify server logic, enabling quick and efficient processing. The front end and the back end work with databases to store and retrieve information. Let's explore a database's role in full-stack development. A database is a software system that stores and organizes an application's data for long-term use. Databases store crucial information like user profiles or product details. A database like SQL Server integrates with .NET applications, making it easy to retrieve data. For example, a shopping app uses a database to remember what's in your cart even after you close the app. Full-stack developers also work with APIs that connect the front end and the database through the back end. An API, or application programming interface, allows different software applications to communicate with each other. It's a structured communication mechanism between the front end and the back end. The back end exposes API endpoints that the front end consumes. APIs allow the front end to request information from the back end, such as product details or user data. For example, when you search for a product online, APIs ensure the database responds with the correct results. Managing all these components requires version control tools to track changes and collaborate. Version control is a system that records changes to a file or set of files over time so that you can recall specific versions later. Tools like Git are used to track and manage code changes across the development team. For instance, one developer might update the back end, while another works on the front end. Git ensures these updates don't conflict, keeping the project working smoothly. In this video, you learned about the components of full-stack development and their roles within an application. Understanding these essential components equips you with the knowledge to create dynamic, user-centered, and adaptable applications. How a web application communicates and organizes its parts determines how efficient, scalable, and user-friendly it can be. By understanding these foundational structures, developers create systems that are both powerful and maintainable. In this video, we'll describe different architectural patterns for full-stack applications such as MVC and microservices. Let's begin by exploring common architectural patterns in full-stack applications. We'll start with monolithic architecture, a cohesive approach where all parts of an application, front-end, back-end, and logic, work together as a unified whole. This simplicity makes it an excellent starting point for understanding how applications are structured. Monolithic architecture programs are single code-based applications with tightly integrated front-end and back-end. Imagine a to-do list app where everything, tasks, UI, and logic, work as a single unit. Each part of the application is tightly integrated with the others, and the application needs to be tested and deployed as a single entity. This approach is great for small projects, but becomes harder to manage as the app grows. For example, when using a monolithic architecture, it's difficult to update one part of the application, like the front end, without fully testing and deploying it. While monolithic architecture emphasizes a tightly integrated approach, the client-server model focuses on separating the front end and the back end into distinct roles. A client-server architecture enables communication between a front-end client and a back-end server. This separation forms the basic structure of how most web applications function, allowing for more flexibility in development and deployment. For example, when you search for a book in a library system, your computer, or the client, asks for the book details. The library database, or the server, responds by providing the information. Understanding the client-server model is essential for establishing communication between components, but efficiently organizing the application's back-end logic requires a structured approach. This is where the Model View Controller, or MVC, design pattern comes in. Model View Controller is a design pattern that separates an application into three interconnected parts: the model, the view, and the controller. This structure helps organize application logic, user interface, and control logic, making the application more maintainable and scalable. To understand how these parts work together, let's break them down. The model handles the data and business logic of the application. The view is responsible for presenting this data to the users, such as displaying product details or a shopping cart. The controller acts as a bridge, processing user input, updating the model, and refreshing the view to reflect the changes. Think of an online store. The model holds product information like names and prices. The view presents those details to users on the website. When you select Add to Cart, the controller updates the cart and ensures both the model and the view reflect this action. This separation makes the system easier to manage and scale. For larger projects, breaking applications into smaller, independent parts can make them easier to work with, which is where the microservices architectural pattern can be used. Microservices are small, independently deployable services that communicate with each other over APIs to perform specific functions within a larger system. For example, a movie streaming platform could have separate services for user accounts, streaming, and payments. This setup makes it easier to manage and scale each service independently. In this video, you learned about different architectural patterns for full-stack applications, such as MVC and microservices. Understanding these patterns equips you to choose the right structure for any project, ensuring your applications remain flexible, efficient, and ready to grow with future demands. Building applications that connect seamlessly between the user-facing front end and the powerful back end is essential for creating scalable and efficient systems. To achieve this, understanding the right tools and framework for full-stack development is key. In this video, we will identify the front-end and back-end tools required for full-stack development, focusing on framework selection. To begin, let's explore some of the tools and frameworks used in full-stack development, starting with Blazor, which allows users to interact with the application. Blazor is a framework that lets you build interactive web applications using C# and .NET. Using Blazor, developers can build a powerful user interface that updates data dynamically, allowing users to have an interactive UI experience. For example, Blazor enables features like filtering products in a catalog. This helps users find products quickly and interact with the app seamlessly. Now let's explore minimal APIs, which power applications and manage data processing. Minimal APIs are a lightweight way to create APIs in .NET and enable server-side logic and routing. They simplify back-end development and connect easily with front-end tools like Blazor. Minimal APIs act as connectors between the front-end and the back-end. For example, they efficiently fetch data like product details, so your app displays up-to-date information. They also need a reliable database management system like MySQL or SQL Server to store and manage application data securely. Microsoft SQL Server is a relational database management system for storing persistent data, and it integrates seamlessly with .NET tools. SQL Server is widely used in enterprise environments for applications that require reliable, secure, and high-performing data storage, like banking systems, e-commerce platforms, and business intelligence solutions. SQL Server secures and makes accessible data like customer details and product inventories, while also enabling features like product searches. Managing databases becomes even more straightforward with tools like Entity Framework Core. Entity Framework Core is an object relational mapper, or ORM, that simplifies interactions between .NET applications and databases like SQL Server. Entity Framework Core acts as a bridge, allowing developers to retrieve or store data with simple commands. It also allows them to work with data as objects instead of writing SQL queries. Finally, let's review how to track your code and collaborate effectively with others using Git. Git is a version control system that tracks changes in code and helps teams collaborate. It allows developers to create, edit, and merge code while maintaining a complete history of every change made to the project. Git is widely used for collaborative software development and is the foundation of platforms like GitHub and GitLab. Now that we've introduced these tools for full-stack development, let's explore how they work together. Blazor powers the user interface, allowing customers to browse and filter items seamlessly. Minimal APIs retrieve the filtered data from the server so that information is accurate and up-to-date. SQL Server securely stores the product information, and Entity Framework makes it accessible whenever needed. Meanwhile, Git helps the development team manage changes to the code, enabling collaboration without the risk of overwriting each other's work or creating conflicts. In this video, you learned about the front-end and back-end tools required for full-stack development, focusing on framework selection. These tools together provide the foundation for building a powerful client-server application. In this screencast, we're going to demonstrate how to configure a full-stack environment with VS Code. So I've got VS Code open and the terminal window ready to go. The first thing I'm going to do is list the SDKs to make sure that I have all the SDKs that I need installed. So I'm going to list the SDKs for .NET. All right, so I have 3 versions of the .NET SDK installed. I'll probably end up using the last one, the 9.0 for the latest version, but I have the SDKs installed, so I think we're ready to go. So the first thing I'm going to do is create a front-end app, a Blazor app. I'm going to use the .NET new command, and I'm going to use the Blazor WASM template. This will create a front-end interactive website with some template code for us, and I'll call that front-end app. So what I'll do now is I'll switch to the front-end app by changing to the folder. And now I'm in that folder, and you can see here I'm in front-end app in the PowerShell link there. So now I can build the application to make sure that we can run it later. And it tells me that it succeeded, so that app is primed and ready to go. We can actually see it in its own instance of Visual Code if we want to by running this command, code dot, and it opens up the front end and we can see the pages and any of the other files that are in that project. This is ready to go. So I'll close that. Now I'm going to go back to my root folder and I'm going to create a server app. I use the web template, .NET new web/o. /o means it will create the folder structure and anything else that it needs to create the app. I'll call this server API. Now I'm going to switch to that application. So that opened it up in its own instance of Visual Studio Code. And now I'm just going to make a slight modification to this just to show how we can start to build this out for a web application. So I'm going to open up program.cs, which is what runs when the app launches. You can see there's already a route here at the /. So if any user just went to the root of the API, they would get a return value of hello world. We're going to add one more route called weather. And this is going to return two values, a temperature of 72 and a condition of sunny. So if a user went to the root of the API and then typed /weather, they would get this value in return. We're going to do one more thing here. I'm going to add a couple of packages that we'll need to connect to a database. The first one I'm going to add will allow us to connect to SQL Server. The second one that I'll add will allow us to use Entity Framework to work with SQL Server data. So this is just downloading the package from NuGet and installing it so that I can use it in the application. I'm going to do the same thing with Entity Framework tools. Just run the .NET add package command, and that's going to install Entity Framework. Obviously, you have to be connected to the internet for this to work, but that's how you install packages in Visual Studio Code. Okay, so now we're going to add the service into the application. So I'm going to use a specific command, add DB context, so that we can actually use the tools that we just installed. Now you'll notice that we're getting some red lines here. That's because we don't have all of the harnesses that we need in place, but this will enable us to be able to work with SQL Server and Entity Framework once we build all the rest of the program out. This just gives us the opportunity to start to use those database options with our application. All right, now we're going to do one final thing. I'm going to close down the server side. This is back to my root folder, so I'm back at my development folder. And so the server and the client are now in subfolders, and I want to add it to a single solution. So I'm going to create a new solution called full stack solution in the root of my folder using a terminal command. So .NET new solution, it'll create as a new item, and it'll be called full stack solution. All right, so the solution file was created, and now I can add my individual items. Okay, so now we've added both the front-end app and the server API projects to the solution, and now we can open up that solution in VS Code. If we look at our solution file, we can see that we've added the front-end app, which is in the front-end app folder, and we can see the project there, and then we've also added the server API project is also in this solution. So now we can treat this as a single solution. We can continue to develop out our front-end app and our server API and build the code so that they can communicate to each other. And we're working with it as a single solution with our individual projects being managed through that solution. And then we can run them individually if we wanted to and have them work with each other. So that's just the basics of setting up an environment so that you can work with a front-end app and a server API, and then you can build the communication tools so that they can interact with one another. In this guided lab, we've got two projects. So I created a folder called Setup Full Stack Environment, and then I created a project called Backend and a project called Frontend using the commands in step 1. So the first thing I did is I made sure that I was in the right folder in the terminal, and then I ran those two commands, and those will create the two projects in their own folders, which is important. So that's step 1, using those commands, .NET new. And then in step 2, it's just having us verify the projects So you actually have to, if you want to run either of them or build either of them according to the instructions, you have to go into the folder for each one. So client or not, cd front end, and then that version not build. And you do the same thing for backend. So you just have to go back out and then cd backend. I'm going to create a separate thing here. I'll get into the client so we can run them separately. So now I've got two terminals open, one for front end, one for backend. All right, let's go back to the backend. That's step 2. Step 3 is setting up the backend API. In the API, this guy here, we got program.cs. The first thing you need to do under builder, this should be here already. Builder services and the var builder should be a part of the code. Below the first services item, and by the way, this may have some sample code in it. I just removed all the sample code. But the things you need to make sure you have is this cores item, because we're calling from the client to the server, from the front end to the back end. And then below var app, the app declaration, you'll have this, which should be here by default. And then you want to make sure you add app.useCores. And then this is where the get route is also put in. So below use cores, you put in your get route, and that's in the step 3 code sample. So just make sure that all those things are there in this specific order. You want to make sure that this is before this and that kind of thing, and make sure all the app declarations are after the app variable has been filled. So that's step 3. And then in step 4, you're going to retrieve the data. So this is where we go to the front end. So now we're going to be in the front end code, and we're going to go to pages, and we're creating a fetch.razor page for this one. And for this code, a couple things to look at is you want to make sure that this port is right. And sometimes you'll have to see what the app runs at. So you'll run the server first. So to do that, I can go in, I'm in my backend, so I can say .NET run, and it'll give me the port number once it loads. So it's 5092. Just make sure that this number is 5092 to run it. I think for the lab, we're just going to leave it as your port number, but I don't know how you want to do that for the lab, but whether you want to put a port number or not. But mine's running at 5092, so I'm just going to leave it be. And I think that's the only thing from the code that we're filling in. The page is /fetch. That's the route. So you need to make sure that's correct. And everything else should be fine. So now that we have that working, I'm going to switch over to front end and run this. And this is running on 5204. So I'm going to open that up, and I'm going to switch to show what that looks like. All right, so I've got the app running, and now I'm going to go to fetch, which was our route. And then it pulls in the items that we had in the server, on the server side. So those are the items that were at our route here, laptop and phone, and that's what we got in our browser. So that's how you set up that lab. Imagine a busy marketplace where vendors and customers interact seamlessly. A RESTful API is like a well-organized marketplace where the front end, the customer, can easily request products, data, from the back end or the vendor. This efficient exchange ensures a smooth shopping experience, or in the case of web applications, a seamless user experience. In this video, we will explain the structure of RESTful APIs and how they facilitate data exchange between the front end and back end. To begin, let's define what RESTful APIs are. RESTful APIs allow apps to communicate over the internet by following shared rules. The REST part is an acronym that stands for Representative State Transfer. RESTful APIs define how data flows between the front end, the part users interact with, and the back end, where the app stores and manages data. This defined system helps apps stay organized and responsive. Now that we understand RESTful APIs, let's explore some of their key components that drive their functionality. We'll begin with endpoints. Endpoints are URLs where APIs receive requests and return responses. Endpoints in a RESTful API are like mailboxes in an apartment building. Each mailbox or endpoint has a specific address or URL where you can send or receive messages or data. You do this using different actions like reviewing, adding, or deleting mail. Just like each mailbox holds specific information for a resident, each API endpoint provides access to a particular resource or set of data. For instance, an endpoint might be a URL like a /products, where an app requests a list of available products from the backend. Now let's explore how HTTP methods guide the API to take specific actions at each endpoint. HTTP methods are instructions that tell the API what action to perform at an endpoint. These methods include get, post, put, and delete. Let's explore the functionality of each of these, starting with get. Get is used to retrieve data from the server without changing the data itself. It simply fetches the requested information. Post is used to send data to the server, often to create a new resource or submit information, which typically results in changes in the server. Put is used to update or replace an existing resource, and in some cases it even can create the resource if it doesn't already exist. Delete, as the name suggests, is used to remove a resource from the server entirely. Now let's combine these in an example. Imagine an e-commerce app in which each HTTP method defines how the product API interacts with data at specific endpoints. Get retrieves a list of products for display. Post adds a product to the cart. Put updates the details of the product, and delete removes a product from the cart. These methods guide the API on how to process data efficiently and accurately. After the app requests an action, the API responds to let the app know how it went. Let's examine how the API responds to the app using status codes. Status codes provide feedback from the API about the result of the requested action. They help both the application and the user understand what happened during the process using numeric codes. Let's explore a few conventional HTTP codes, starting with a 200 status. A 200 status code indicates success, meaning the request was processed correctly. Everything went as expected. A 404 status code means not found, indicating the requested resource doesn't exist, like when a user tries to access something that isn't available on a server. A 500 status code signifies a server error, meaning something went wrong on the server's end while trying to process the request. Status codes enable developers to diagnose issues and manage responses efficiently. For example, if you try to access a product page that does not exist, you might receive a 404 error. It also allows a developer to diagnose the error quickly by understanding the source of the issue. A final component of RESTful APIs we need to examine is payloads. The payload is the actual data the app sends or receives during an API call. The app formats this data in a way both the front end and the back end can understand, such as JSON. For instance, when you review a product online, the payload contains its name, price, and description, all the details the front end needs so it can display the item to you. In this video, you learned about the structure and components of RESTful APIs and how they facilitate data exchange between the front end and the back end. By understanding RESTful APIs, you unlock the potential to create smooth and efficient data exchanges that power every app interaction. APIs are the hidden foundation of digital services, allowing software to interact and exchange data seamlessly. Today, they are essential in everything from mobile apps to e-commerce platforms. In this video, we will explain the structure and purpose of RESTful APIs within the .NET Minimal API framework. APIs come in different types. RESTful APIs are unique because they follow specific rules and are stateless. Stateless means that each request a client makes to an API is independent. This design makes them scalable and efficient. Now let's explore the key components of RESTful APIs, starting with endpoints. Recall that endpoints are URLs where APIs receive requests and return responses. Endpoints are like addresses for specific tasks. For example, HTTPS mydomain.com/products can list items for sale, and HTTPS mydomain.com/orders can handle new orders. This organization makes APIs clear and predictable. To send or receive data using endpoints, developers use HTTP methods. HTTP methods specify the type of action that a call to an API endpoint will perform. The four primary HTTP methods are GET, POST, PUT, and DELETE. These standardized actions enable developers to interact with information using API endpoints. An application uses the GET method to retrieve information from a server. For instance, when a client application makes a request to mydomain.com/products endpoint, the server application routes the request to the GET action to retrieve a list of items without changing the data. Adding new data to a data store is done with the POST action. For example, submitting an order to the mydomain.com/orders endpoint will route the order to the POST action, which saves the order information to the server. PUT updates existing data. Adjusting an order's quantity through mydomain.com/orders order equals 1 modifies the record on the server with an order ID of 1. The parameter specified with the question mark sends the order ID to the endpoint so the PUT action knows which order to update. The delete method removes data. If you cancel an order, the application can call the mydomain.com/remove order equals 1 endpoint, which deletes it from the system. Like the PUT endpoint, the client application has to specify the order ID in the URL so the delete endpoint knows which order to delete. After interacting with an API, it's helpful to confirm whether the request is completed properly, which is where the status codes are useful. Status codes are numerical codes that indicate the outcome of an API request. Status codes 200, 404, and 500 inform the calling application whether the API call was successful or whether an error occurred at some point in the process. A 200 status code confirms the request was successful. For example, when retrieving products, the server provides the data and a 200 code to the client application. A 404 code indicates that the request resource is missing or not found. When a client requests a resource, like a web page or an API that doesn't exist, the server returns a status of 404. The client application can listen for this code and take the appropriate action. A 500 code communicates that the server encountered a problem while processing the request. Because the cause of this error can be a wide range of issues, the client application needs to respond gracefully, even though it may not know exactly why the error occurred. Next, let's explore payloads, which are essential to how RESTful APIs and the .NET Minimal API work. Payload is the data exchanged between the client and server, often formatted as JSON. In other words, when an HTTP request is sent to an endpoint, the API processes it and responds with the status code and the data requested or updated. When submitting an order, details like the product ID and quantity are included in the payload. For example, an order with product ID 5 can contain quantity 2. Applications use JSON format, which makes data easy to read and process. The server may also send a payload back to the client in JSON format. Finally, let's examine dependency injection, which is how developers structure APIs to perform all the tasks the application needs. Dependency injection, or DI, is a programming pattern that involves providing an object with its dependencies rather than having the object create them itself. This promotes loose coupling between objects, making code more modular, testable, and maintainable. Dependency injection streamlines development by providing reusable services automatically. For instance, using DI, a developer can reuse a logging service to track API activity without requiring developers to create the same service over and over. In this video, you learned about the structure and purpose of RESTful APIs within the .NET Minimal API framework. RESTful APIs rely on endpoints, HTTP methods, status codes, payloads, and dependency injection to create efficient connections between systems. Data is indispensable to every modern application, and JSON is the language that allows seamless communication between systems. With the system.text.json library in .NET, you can efficiently handle JSON data, ensuring smooth interactions between the client and the server. In this video, we'll demonstrate how to use system.text.json to serialize and deserialize JSON data in .NET Minimal APIs. Let's begin by defining system.text.json and exploring its role in serialization for JSON data in .NET Minimal APIs. The system.text.json library is a lightweight, high-performance library for handling JSON data in .NET. This library comes pre-installed with .NET Core 3.0 and later versions, so no extra setup is required. Now that we understand what system.text.json is, let's explore JSON serialization's role within it. When working with JSON data, you need to structure it using a data model. A data model is essentially a blueprint that defines the relationship each item of data in your dataset has with other items. Data models are helpful because they provide a clear blueprint for organizing, defining, and standardizing data. For example, if you're working with a product catalog, you might create a product class with properties like name, price, and description. In this simple data model, you know that the three properties are part of the product object and don't stand alone. Once your models are defined, the next step is to translate them into a format that can be shared between the client and the server, otherwise known as serialization. Serialization is the process of converting an object in an application to structured data such as JSON or XML. Serialization is important because it allows complex data structures or objects to be converted into a format that can be easily stored, transmitted, and reconstructed later. This ensures efficient data storage and communication across systems. After serializing data for transmission, you'll need to convert it back to an object that your client or server code can use using deserialization. Deserialization is the process of converting structured data such as JSON or XML back into an object or usable data format in an application. For example, when a user submits a registration form, the server receives the data in JSON format. Deserialization transforms this data into a user object that the application can process. To ensure serialization and deserialization work smoothly, you may need to configure serialization settings like naming policies and ignoring null values to align data formats between the front end and the back end. For example, if your front end uses camel case naming like product name, you can configure serialization to follow the style for consistency. You can also ignore null values to reduce the size of JSON payloads, improving performance during data transmission. In this video, you learned how to use system.text.json for serializing and deserializing JSON data in .NET Minimal APIs. By using the system.text.json library in .NET, you're not just managing data. You're enabling the systems you build to communicate effectively and deliver seamless user experiences. So I have here a very simple .NET Web API application. I put all the routes in program.cs so it's easy to work with. What this application is going to do is set up some endpoints that we can call. We're going to use Postman to test. All of our routes are set up here below all the context that we have to include for our application to run. So we have a number of endpoints. I'll walk through each of these individually. The first is a get endpoint. So we use the get method in Postman to retrieve data using this endpoint. The endpoint is /counters. And all this is going to do is return any of the counters that we have set up and that we've used using the post method below. So we're going to essentially add some counters to an in-memory database, and this get method will retrieve whatever counters we've added. The next one is a get method as well. You can see app.mapGet, and this method will retrieve a counter, an individual counter by name. So you can see the route is /counters/ and then In the brackets, there's name, and we would pass in the name from Postman to our endpoint. And then this get method will look up, it will find the first or the default counter that's in our list where the name equals the name that we passed in. If the counter isn't null, it returns the name of the counter with all the other data associated with it. Otherwise, it will return not found. The next endpoint is a post, and you can see it's the same endpoint name as the get that we had above, /counters, but because this is a post endpoint, the application will treat it differently, and .NET will know what to do when we send a post command using the post method versus a get command, even though the endpoint's the same. So here what it's going to do is take in that request that we send. We're going to send in a body. You'll see this when we do the test. We're going to send in some data in JSON format. And first of all, it's going to check to make sure the string isn't null. If it is not null, then it will extract the values from the request body that we send in. It'll first check to make sure that the name that we're sending in doesn't already exist. And if it doesn't, then it's going to add to our database value counters. It'll add the body, the data that we send in, and then it'll save all the changes. It'll also return the fact that the counter has been created and provide us with the data that it retrieved from that request that we made. So this is a post method, meaning we're sending data, and then this method will do something with that data. And then the final method is another post method, and you can see this route is /counters. There's the name in brackets again, and then another part of the route is /increment. So we're going to pass in the name of the counter that we create, and then this will essentially look for that name and increment the count in the counter value by 1. So whatever we pass in, it will increment that by 1, and then it'll save the changes and then return back to us the counter information with the new updated count. So again, this is a post. We set that route very specifically to do work with the data that's already in memory database. Obviously, if we try to pass in a name here and it doesn't exist, then the method will fail and we won't get the results that we want. So I'm going to go ahead and run this API. And we can see that the API is running at localhost 5091, so we can use that as our root. And then in Postman, we'll send in our statements with that route. So we can see we have localhost :5091, which is what Visual Studio Code said it was running at. And then there's our route. So we're going to use the get method. So Postman allows us to request with all different kinds of methods. We're going to use the get method first on counters. So in our application, that's going to be this route. So app.mapGet /counters. And you can see we have mapGet, which is the get method, and the counters route. So when we send that in, you can see we get a response back. So the status is 200, which means that it did hit the API, it found the method, and it returned what it was supposed to return, which is nothing, because we haven't created a counter yet. So even though we were able to use the endpoint, because there were no counters in the database, it returned nothing, which is what we expect. Now I've got another tab up here with the post method. And remember in our application, we saw that there's the post method here, also /counters. And this is going to allow us to pass data to the application and save data into the database. So in this method, we're using this body tab to essentially send in JSON data. So in this JSON, I have a name and a count, which I'm passing in to that method. The counter is named counter1, and we're going to start the count at 1. So when we send this request, we're going to send that body to the post method here. It's going to take that request, which is noted here, and then it will populate the counters db.counters data with the counter information that we send in. So let's go ahead and do that. So it worked. We got a 201, which means that the record was created. The record has an ID of 1 and a name of counter1 with a count of 1. And we can create a second one easily enough by just changing our body data. So we have counter2, so we'll send that in. Counter2, which has an ID of 2 and a count of 1. Now if we go back to our get method that retrieves all of the counters that we have, when we send that in, we now have our 2 counters because that's now in the database. It's an in-memory database, but as long as the program's running it, it will stay in there. And so now we have our 2 counters, each has a count of 1. All right, let's go to our fourth method. This is our increment method. So we can pass in our counters slash counter1, which is the name. You'll recall from our application where we post to the increment, we have to pass in the name. So we know that we have a counter with the name of counter1, which is here. So we're going to pass that into the URL. We're going to finish off the route with the increment slash increment at the end of the route. When the request is made, the API will take that name, look up the name, and then hopefully increment the counter by 1 when we send that in. So we'll go ahead and do that. So now you can see the count is 2. So its counter1 has a count of 2 because we're incrementing that count by 1. So we're going to take whatever number it currently has in the database, increment it by 1, and then send that back, and that will be stored. So when we do db save changes async, the increment will be saved in the database. And we can continue to send, and it'll just continue to increment the count. So now it has a count of 8. So if we go back to our get method and retrieve all of our data, we should have counter1, which has a count of 8, and counter2, which has a count of 1. And that is how you create endpoints. This is a very simple API application, and we're using Postman as a good tool to test whether your APIs work. And then obviously you can build a front-end application that could interact with these APIs in much the same way that Postman does, but you would build a user interface so that users can interact with that API much more easily. For this guided lab, we're going to be using a web API from the template. And I've used this command, .NET new web API-O, and then I've already got the project set up, but this is how I set it up, GL RESTful API. You hit enter, and then it'll create the project for you. You can use the command code and whatever the project name is, so it's going to be code GL-RESTful API. And then when you click enter on that, it'll open up the project in a separate window. In step 1 of the project, we're just adding some dependencies into the program.cs file. You see it's got builder services, add controllers here at the top. That's the first item you need to add. And then there's app builder.build, which should be already in the template. Add the app use routing command. And notice that the app.use routing has to come after the app declaration, so after var app. And then I've got app use endpoints, which also has to come after the declaration of our app. And then you just have to make sure all that stuff is above app.run when you're putting the lab together. In step 2, you're going to create a counter.cs file. So just click this little button, and it'll give you the opportunity to create a new file, and you're going to call it counter.cs. And in there, you're going to add the class. So just copy and paste the class in. In step 3, you're going to implement the endpoints. So now we're going to go back to program.cs, and the endpoints are here. I put it after use endpoints, and it seems to work fine. By the way, if you have app.use HTTP redirection, if you want to get this to actually run, you have to comment that out because that uses HTTPS, but you need a certificate for that, which we don't have. So just comment that out. It'll work fine. So you're going to add the var counters, new list counter, and then the 2 routes, app post slash counters, 3 routes at the get route slash counters, and then the post counters name increment. And those go before app.run. So those are just set up the routes for the application. All right, then to run it, if you need to test it, just do that run. It's going to run on a specific port, HTTP localhost 512. And now I'm going to switch over to Postman to test it. So to test it, we're going to first post to localhost counter. So you can see in Postman, I've got the post call, the post command. And then in the body, so I've selected the body tab and then selected raw. You have to put this JSON in there. So I'm just using a very simple one, name sample. And then click send, and it should send it. 404 not found. Oh, I probably have the wrong, hold on 1 second. I just put the wrong route in there. So it's counters, not counter. All right, so when I do that, it created the sample. Now I can do sample 2, send that. Okay, so now I've got 2 samples in there, and you can see it updates the ID. And then I'm going to go to another tab where this is the get route. Again, I need to put in counters here. And it should return both of those samples that I put in. So now we have sample 1 and sample 2. And that's the route that was the get call. And now the really essence of this is updating the counter using that call. So I'm going to go to the third tab here, which is also a post. And you can see I have, oops, I forgot to put counters in again. So let me add counters to my route. And then this sample 1 is the name of just one of the samples that I added. Remember, I added sample 1 and sample 2. This is just one of the names. You can use either one. And then increment. And when I send that, you can see it updated the count to 1. And if I keep clicking send, it'll just keep updating the route. And that's really what the little app is supposed to do. So that's the essence of it, to set it up and to test it for this guided lab. APIs power modern applications by connecting backend data with the user interface. Creating APIs for front-end applications involves designing, implementing, and securing endpoints to deliver the required data efficiently. In this video, we'll describe the process of creating APIs that serve front-end applications by exposing necessary data. Let's begin with the first step in creating an API, defining front-end needs. Developers must define the data requirements for each part of the user interface to ensure the API provides the right data for the front end to display and interact with seamlessly. For example, when creating an API for an online store, the front end might display to the user the product name, as well as a product description, its price and availability, and an area for customer reviews. The API needs to provide this data to ensure the front end can display a completed product page. By clearly defining these requirements, the API delivers the right information to create a seamless user experience. Now that we know what data the front end needs, it's time to define the endpoints. Recall that endpoints are URLs where APIs receive requests and return responses. They allow the front end to request and retrieve information from the back end. For instance, an online store might use one endpoint to retrieve product information and another to fetch customer reviews. Each endpoint provides the front end with a direct route to access specific data. With endpoints in place, developers must structure responses so the front end can interpret them efficiently. While APIs can use various formats like XML or YAML, JSON is the most widely used format today. JSON organizes data into keys and values, creating a clear communication structure between the backend and front end. For instance, a product's attributes like name, price, and availability, or stock status, become keys, while its details are the values. This structure makes JSON an efficient and reliable format for API responses. We'll decide on a consistent structure for the data our API returns to keep responses predictable. Using a consistent format makes responses predictable so the front end knows what data to expect and can process it easily. Like a product, each data item is represented by a set of attributes like name, price, and category. This consistent structure allows the front end to display information accurately. To keep responses efficient, we'll remove any unnecessary data. For example, if the front end only requires product names and prices, we'll remove additional fields to make the response more efficient. This reduces the amount of data transferred and keeps responses quick. Now that we've structured the API responses, let's address how to securely connect the front end and back end by implementing cross-origin resource sharing, or CORS. Cross-origin resource sharing is a security mechanism that determines whether a front-end application hosted on one domain can interact with an API hosted on another domain. Since the front end often operates on a different domain other than the API, we need a way to safely allow data requests between them. CORS manages this by restricting access, ensuring that only trusted sources can reach the API. Implementing CORS involves configuring headers to allow requests from approved sources like your front-end application. This step limits access to trusted domains, protecting your API from unauthorized use. To enhance security further, we can restrict the types of requests that front ends can make. For example, limiting requests to read-only operations prevents unauthorized server data changes. In this video, you learned about the process of creating APIs that serve front-end applications by exposing necessary data. Keep these principles in mind as you design APIs that combine the data and user experience, making information easily accessible for front-end applications. APIs are the invisible engines driving modern web applications, enabling them to interact with powerful backend systems. Integrating APIs in Blazor applications empowers you to create dynamic, data-driven user experiences. In this video, we will explain the process of creating and consuming APIs in Blazor applications, focusing on leveraging the HTTP client and binding API data to user interface components. To begin, let's examine the steps for integrating APIs in Blazor applications, starting with setting up HttpClient to enable API calls in that application. Remember that HttpClient is a component used in Blazor to make API calls. First, we register HttpClient in the project to enable communication with external APIs. Once registered, HttpClient can be injected into a Blazor component to fetch data. For example, in a weather app, using HttpClient enables you to get JSON data using an API call. The data can return information like the current temperature from an external service. It works like a messenger, retrieving and returning information to your app for display. Now that HttpClient is ready to make API calls, let's examine how the data it retrieves is formatted as JSON data so your app can use it. JSON organizes data into a readable format, making it easy for your app to process. For instance, a weather service might send data where the key temperature is assigned the value 72 degrees Fahrenheit. In this example, temperature is the key or the container that holds the data, and 72 degrees Fahrenheit is the value assigned to that key. In JSON, the key and the value are separated by a colon, which represents their relationship. And this is the basic structure of JSON data. Next, JSON is transmitted using API endpoints, which are the gateways for sending and receiving information. API endpoints are URLs where APIs receive requests and return responses. Creating API endpoints involves defining the endpoints to fetch the data needed for user interface updates. In the backend, endpoints route to methods that handle HTTP requests like GET or POST. For example, the URL mydomain.com/weather endpoint may route to a GET method that retrieves temperature data for the weather API. Once the data is retrieved through API endpoints, the next step is to bind it to the app's components for display. Binding data to components involves displaying the API data dynamically in Blazor components. The data is returned to the client in JSON format. The client then deserializes the JSON into an object the application can use. Blazor can then reference the object's properties. Suppose a weather app client deserializes JSON weather data from an API into an object called forecast. Blazor can bind the forecast object to specific user interface elements using the @ symbol. In this example, @forecast.summary references the summary property of the forecast object. Sometimes APIs may be unavailable or return invalid data, which is where error handling occurs. Error handling in Blazor involves techniques for managing API failures gracefully in Blazor. Wrapping API calls in try-catch blocks ensures your app handles errors gracefully. For instance, if the weather service is down, your app can take alternative actions without crashing. Also, instead of leaving users without explanation, you can display a feedback message like, "Weather data is currently unavailable, please try again later." This helps users understand the issue and encourages them to try again. In this video, you learned about the process of creating and consuming APIs in Blazor applications, focusing on leveraging the HTTP client and binding API data to UI components. Integrating APIs in Blazor applications is more than just fetching data. It's about connecting the dots between user interfaces and the data that powers them. When you think about how a lot of data gets transferred to and from client devices like web browsers or applications, a lot of that happens over the internet using APIs or application programming interfaces. In this video, we're going to demonstrate how to consume APIs in a Blazor application using HttpClient, and we're going to bind the data to UI components. So I have a Blazor application already prepared. In this screencast, I've already set up the Blazor application using the .NET new and the Blazor WASM template. So I used that command and set up this Blazor application and then made some changes to some files in the application. And we're going to walk through in this screencast what's in these files and how they work. What we're going to do in this application is call out to an API and retrieve data from that API using HTTP post to do that. So you can see at the top of this Razor file, this fetchdata.razor file that I've created in the pages folder, we have some HTML, and it's using Blazor directives. It's got the if directive and the for each here to retrieve data and then get posts back from this API. So we're just creating the individual elements here that we need to display the data that we're getting back from the API. And that's what's in the top of this Razor file. If the data has not been retrieved in the else statement, we're just showing a loading message. Next, we have our @code directive, and here's where we put all of our C# code. So the first thing we do is set up a list of posts, and post is a specific object that I created, and that's at the bottom of this file. You can see we have a post class, and it has three elements in it: an ID, a title, and a body. The ID is an int, the title is a string, and the body is a string as well. So when we get the data back from the API, we're going to put that data into this post object, and we're going to put it into a list because we're going to get multiple posts back from the API. So we've created a list of these post objects, and we're just naming that variable post. Then we have this onInitialized async method. This runs when the page loads. So anytime the page loads, it's going to run this method, and it'll run the code obviously inside the method. You'll notice that it's an async method. So if we want to retrieve data multiple times from the API, the async method will allow us to do that in the background, and it can actually queue up tasks. So it can make this call, this onInitialized async call multiple times, and when one is done, it'll do the next one and so on. So that async tasks allows us to keep the application responsive while it's making the call to the API. The next thing we've done here is to retrieve the data. We're going to fill that list of post objects in this post variable. You can see we use the await keyword to make sure that we're waiting for the request to finish before going on to the next request. And then we use the method get from JSON async. So the HTTP object is the harness that we're using, and the method on the HTTP object get from JSON async is what retrieves the data from the API. And then part of that method, we pass in the URL for the API that we want to retrieve from. So this is a get call, and we're passing in the JSON placeholder.typicode.com/posts. And so this was just a test API that we can use to retrieve data from a remote API. When that is filled, then these items will automatically get updated because we're using these Blazor directives. So once the post is filled, then it will, the post variable is filled, then it will go through and post that to the website. We can actually see the data. So that's what we're going to do first, and I'll demonstrate how that works. We'll run this application. It will build, and then we can browse to this location. And you can see we're not on that page yet. This is just our Hello World landing page. So we'll put in our path here, our route. So this goes to the fetch data page, which we created. And you can see we have our ID, our title, and our body. And this is all obviously fake data. It's just demo data. But it has retrieved that data from the API, from the remote API on the internet, and populated that posts variable, and then filled our elements in our HTML section with the data that are retrieved from the API. Let's go back to our code. The other thing that we've done here is we've put the request in a try-catch block. In case something goes wrong, we want to be able to fail gracefully. There's a lot more we could do here to make the user experience a little bit better, but I'm just for demonstration purposes, just put it in a simple try-catch block that writes out the error to the console. I'm going to change this URL to something that doesn't exist, and then we can run the application again, and we'll see if it hits that try-catch block. So I'm going to go back to my web page. When I refresh, it'll show the loading message because it's never actually gotten to the ability to fill that data. When it hit this line of code, this line 41, it didn't find the endpoint, so it created an exception, and then it wrote out to the console. We can take a look at that by going to DevTools. I'm going to show you very quickly how we can analyze what happened here. So you'll notice there's our message, error fetching data. And then you can see in the code, we have the exception message that's going to print out as well. So it's error fetching data, and then it gives us the message that it received back from the API call. And the message was response status code does not indicate success. It was a 404 error, and a 404 error means not found. So it did hit that catch clause and produce that message to the console. So this is a very simple example of how you can use these API calls in a Blazor application to call out to a remote endpoint, receive data back, and then fill HTML elements using the data that you get back from the API. In this lab, we'll be implementing API consumption in a React-based front-end application by retrieving and displaying data from a back-end service. I have a Blazor application set up here. It's using the Blazor Wasm template. I've got a specific Razor file that I've created, fetchdata.razor. Other than that, this is mostly the template code. In step 1, we're configuring the HTTP client. This should be prepared by the template. In this case, we'll be adding the base address, and that is going to equal new URI builder.hostenvironment.base address. And you can see we're using the builder object here that we created from the WebAssembly host. And this just creates the environment so that we can use the HTTP client in our application. In step 2, we're creating the Razor component that will fetch the data from the API, and that's called fetchdata.razor. Here up at the top, we've got our HTML block using Blazor directives to populate a table with weather data that is retrieved from an API. In the code directive, down below, we've got the C# code that we're going to use to retrieve data from the backend service. Now in our HTML, we've got a for each loop. So this is going to take the object that's been populated, the variable that's been populated with the weather data from the remote service. And that weather data is declared here in the C# code. So we're creating a list of weather forecast objects called weather data. We're iterating through that. And then each item in the table is going to be from the weather data object. So you can see we're creating a variable data for each item in the list, and then we're going to populate it with the 3 items from the object. That object is declared below in the class weather forecast. You can see we have date, temperature, and summary, and those are the 3 items that we're using here in the for each loop to populate our HTML. Down in the weather forecast object, you just have to make sure that the individual items that we're using for each of the attributes in the weather forecast class match the items that we're populating and getting our data from the API. So when we populate our HTML, it should match what was in the object. In our API call, which we're doing in our try catch block here, we're populating the weather data object with the results from the API call that we're making. Notice that it's just /weather forecast here. Typically, this would be a full HTTPS URL, but we're simulating a remote call with this /weather forecast. So here we're just going to go to an endpoint that is /weather forecast, and whatever the result is from the GET call, it will populate weather data, and then that's what we're going to use up here to populate our HTML. And that's really it for this lab. These are the fields that you need to populate. And by using this approach, you can retrieve data from an API and populate HTML elements with it in Blazor. Front-end and back-end integration drive application functionality, managing processes like payment transactions and real-time updates. Understanding this interaction helps developers build efficient, high-performing systems. In this video, we will identify common scenarios where front-end and back-end integration is critical to application functionality. Recall that in applications, the front-end manages the user interface, while the back-end processes data, manages storage, and ensures system functionality. APIs facilitate communication between the two, enabling data exchange. Let's explore some real-world use cases to better understand the practical implications of front-end and back-end integration. One of the most familiar ways front-end and back-end integration works is in e-commerce applications. E-commerce applications are software platforms that enable users to buy and sell goods or services online, manage transactions, inventory, and user interfaces for shopping experiences. In e-commerce applications, the backend handles inventory management, payment processing, order tracking, and database operations to ensure seamless transactions and logistics. The front end provides user-friendly interfaces for browsing product catalogs, adding items to a cart, and completing checkout. For example, when you add an item to your cart, the front end displays the update to the cart. At the same time, the back end reduces inventory and prepares it for checkout. Social media platforms also rely on front end and back end integrations to connect user interactions with stored data. Social media platforms are online services that facilitate user interaction and content sharing through posts, messages, and multimedia across personal and professional networks. With social media platforms, the backend manages user accounts and handles real-time notifications, while the front end displays user feeds, including images and videos. APIs manage user data, posts, and real-time notifications between front-end interfaces and back-end services. For example, when you like a post, the front end updates the like count instantly, while the back end stores this interaction to keep it accurate across devices. Streaming services use a similar front end and back end integration method to deliver content to users efficiently. Streaming services are digital platforms that deliver audio or video content in real time over the internet. This allows users to access entertainment without downloading. Streaming services rely on the front end for features like search and playback controls, while the back end manages media storage and streaming. For example, when you press play on a movie, the back end streams it at a quality optimized for your internet connection, while the front end offers playback controls. This collaboration maintains an uninterrupted experience for the user. Finally, businesses use enterprise applications with front-end and back-end integrations to make data-driven decisions. Enterprise applications are software systems designed to support and integrate business processes such as resource management, customer relationship management, and data analytics within organizations. In most enterprise applications, the backend integrates databases and analytic engines and secures APIs to process business data and support decision-making. On the front end, employees can access dashboards, reporting tools, and user interfaces that provide insights and help to manage workflow effectively. In this video, you learned about common scenarios where front-end and back-end integration is critical to application functionality. Whether it's e-commerce, social media, streaming, or enterprise software, these integrations power our daily experiences. By recognizing how these systems work together, developers can create more efficient, user-centric solutions that drive business success. Front-end and back-end components actively communicate to power interactions on your favorite apps and websites. Working together, they deliver the advanced functionality that drives modern user experiences. In this video, we will describe project-based examples of how front-end and back-end components interact to deliver complex functionality. The first project we'll examine will focus on API gateways. An API gateway manages multiple APIs between the client and back-end services. API gateways simplify how multiple APIs work together to manage a variety of client requests and direct each request to the correct back-end service, acting like a traffic controller for data. For example, when you shop online, the system retrieves product details, updates inventory, and processes payments from different back-end services. The API gateway routes these requests correctly, creating a smooth shopping experience. After the API gateway routes requests to the appropriate services, authentication systems verify that only authorized users can access secure areas, like accounts or payments. Authentication systems use front-end forms to validate users through back-end authentication services. They restrict access to sensitive areas of an application by allowing only authorized users. For example, when signing into a telemedicine app, the system first needs to verify your identity before granting access to any sensitive medical information. Authentication systems protect your data while allowing only verified users to access restricted features. After authenticating users, single-page applications, or SPAs, deliver fast and responsive content by dynamically loading content without requiring page reloads. With single-page applications, the front end communicates with the back end using APIs for dynamic content loading. SPAs speed up web experiences by loading dynamic content through APIs without refreshing the entire page. For example, when users scroll through a social media feed, the app loads new posts automatically, maintaining a continuous experience without interruption. This reduces waiting time and helps users stay engaged. While SPAs improve user experiences, microservices-based apps support scalability behind the scenes. Microservices-based apps are apps where different services communicate through APIs and are integrated seamlessly with a unified front-end interface. Microservices divide application functionality into smaller independent services, each responsible for a specific task. For example, in a food delivery app, one service manages payments, another tracks orders, and a third manages the menu. These services communicate through APIs, ensuring flexibility and reliability. When one service needs an update, the others remain unaffected, which is why this architecture supports managing complex projects. In this video, you learned about project-based examples of how front-end and back-end components interact to deliver complex functionality. Understanding how front-end and back-end components interact lays the foundation for building real-world solutions that meet complex user needs. In this module, you have taken a significant step towards mastering full-stack development by learning how to seamlessly connect front-end and back-end components. These skills are critical for building cohesive, dynamic, and user-friendly applications. We began by exploring the architecture of full-stack development, breaking down how front-end, back-end, and database components interact. Understanding this architecture is essential for creating scalable and maintainable applications that meet user expectations and business needs. Next, you discovered how to set up a robust development environment, configure essential tools, and manage dependencies. A well-prepared environment not only minimizes errors, but also ensures a smooth and effective workflow, laying the groundwork for successful development projects. We then focused on building RESTful APIs, the backbone of communication between the front end and the back end. Designing efficient and secure APIs equips you to create powerful, data-driven applications that meet modern standards of scalability and reliability. After that, you learn to integrate APIs into front-end applications, enabling dynamic data handling and real-time interactivity. This step is crucial for delivering seamless user experiences and bridging the gap between static design and responsive functionality. Finally, we explored real-world examples of full-stack integration, analyzing how successful applications combine front-end and back-end components to create impactful user experiences. These case studies demonstrate the practical value of your skills and inspire you to implement them in meaningful ways. Congratulations on completing the module connecting front-end and back-end components. You've gained essential skills for creating seamless full-stack solutions, setting the stage for success in modern application development. Keep building, integrating, and refining your abilities as you move closer to becoming a confident and proficient full-stack developer. Welcome to Consuming APIs in Blazor applications. In this module, you'll learn how to integrate APIs into your Blazor projects, make and handle API calls, implement asynchronous programming, and follow best practices for API consumption. By the end, you'll have the skills to create dynamic, responsive applications powered by robust API integrations. We will begin by defining the fundamentals of API consumption in Blazor, establishing a clear understanding of how APIs enable dynamic, data-driven applications. This lesson will cover the basic principles of working with APIs in Blazor, ensuring you understand the key role APIs play in modern web development. By laying this foundation, you'll be better prepared to connect your applications to external data sources and unlock their full potential. Next, we will explore how to make API calls in Blazor, focusing on techniques to fetch and display external data effectively. You'll learn how to initiate API requests directly from your Blazor application using HTTP clients and other tools. This skill is essential for creating applications that can retrieve and display real-time data from external services, enhancing interactivity and user engagement. Then we will examine how to handle API responses in Blazor, learning to process and display data in ways that enhance user interaction and application performance. This lesson will teach you how to parse and utilize API responses, ensuring that raw data is transformed into meaningful, user-friendly information. Understanding how to handle responses is critical for maintaining a seamless user experience and building reliable features. After that, we will learn about asynchronous programming in Blazor, mastering techniques that ensure your applications remain responsive while managing API interactions. You'll explore the concept of asynchronous programming and how it applies to Blazor applications, particularly when working with APIs. These techniques allow you to perform tasks like data retrieval without freezing the user interface, improving both functionality and performance. Finally, we will discuss best practices for API integration in Blazor. We'll cover key strategies for optimizing performance, enhancing security, and ensuring maintainability. This lesson will provide practical guidelines for making your API integrations robust and efficient, from error handling to secure data transmission. By following these best practices, you'll build Blazor applications that are reliable, scalable, and ready for real-world use cases. By the end of the Consuming APIs in Blazor Applications module, you'll have mastered the essential skills to integrate APIs seamlessly into your Blazor projects. You'll know how to connect your applications to external data sources, make API calls, process and display responses, and implement asynchronous programming techniques to enhance user experience and application performance. Additionally, you'll have a solid understanding of best practices to ensure your API integrations are secure, efficient, and maintainable. With these skills, you'll be fully equipped to create dynamic, responsive applications that leverage the power of APIs to deliver real-time functionality and robust data handling. Let's dive into the module and unlock the full potential of API integration in Blazor. Modern apps are powered by seamless connections to external data, whether they pull in weather updates or manage product inventories. Blazor makes these connections dynamic and efficient, opening up possibilities for interactive and responsive applications. In this video, we will define API consumption and its role in data services integration with Blazor components. To understand how this works, let's define some key terms starting with API consumption. API consumption is the process of retrieving and using data from external APIs within an application. Apps consume APIs to connect with external services and get data like weather updates or stock prices, making them dynamic and interactive. While API consumption retrieves the data, Blazor components manage how that data is organized and displayed within the application. A Blazor component is a reusable, self-contained piece of code that manages the user interface or UI, the logic, and state for specific parts of the app. For example, a reusable product card component in an online store can display product details dynamically without writing separate code for each product. Finally, to ensure that the data in the UI stay in sync, we use Blazor data binding. This keeps the user experience smooth and responsive. Data binding is a mechanism that synchronizes data between the user interface and the underlying application logic, so changes in one reflect in the other automatically. For example, a shopping cart updates the total price as users add items, keeping the UI and the data in sync without refreshing the page. These features integrate into Blazor applications to fetch, process, and dynamically display data. Let's explore how you could integrate an API call in a Blazor app, which involves 4 steps. First, you identify the API endpoint by finding the external service that provides the data you need. Next, you write Blazor code that sends a request to the API by asking the service for the data you want. For example, you might write code that retrieves product details or weather updates from a service using an API endpoint. Next, the API processes your request and sends back a response containing the data your app needs. You process the data by transforming it into a format your app can use, like a list of items or a weather report. Finally, you display the data by using Blazor components to provide the information you processed in a dynamic and user-friendly way. In this video, you learned about API consumption and its role in data services integration within Blazor components. Blazor's ability to seamlessly integrate APIs with dynamic components transforms how applications manage and display data. APIs are the core of modern applications, connecting your software to a world of dynamic data and services. Understanding how to integrate APIs into Blazor applications unlocks the potential to create interactive, real-time experiences for your users. In this video, we will identify the essential components involved in integrating APIs into Blazor applications. Integrating APIs into Blazor requires 3 main concepts. Let's examine each concept in detail, starting with HttpClient. Blazor uses HttpClient, which is a Blazor component used to make HTTP requests to APIs. HttpClient is the tool that enables your application to communicate with external APIs by sending requests and receiving responses. For instance, HttpClient acts as the messenger in a weather app that retrieves today's forecast from an API. To manage HttpClient effectively, Blazor uses a concept called dependency injection. Dependency injection, or DI, is a programming method that gives a class the tools, like services or objects, it needs to do its job without the class having to include those tools itself. DI is used to ensure that the HTTP client is available and properly configured for all your application's components. Think of DI as like a shared coffee machine in an office. Everyone can use it instead of setting up their own. By integrating HTTP client using DI, each part of the application will have easy access to the component whenever they need to communicate with the APIs. The next concept is making data usable for the application using JSON deserialization. APIs often deliver data in JSON format, a standard for efficiently transmitting the information. However, raw JSON isn't directly usable by Blazor. It must first be deserialized into objects that the application can process and use effectively. Deserialization is the process of converting structured data, like JSON or XML, back into an object or usable data format in the application. After receiving data from an API, deserialization transforms the data into a format your app can use and display in a meaningful way for your users. For example, a shopping site might fetch a list of products in JSON format and use deserialization to create a products object. This object can then be used to display product names, prices, and availability on the site. Once the data is ready for use, the next step is deciding when and where in your application's flow to process and display it. To make this decision, you need to understand component lifecycle methods. Every Blazor component has a lifecycle, which includes stages like creation, rendering, and removal. Developers can use lifecycle methods to fetch and render data when it's most appropriate. Component lifecycle methods are predefined methods that allow developers to run custom logic at specific stages in a component's lifecycle. This creates a more seamless user experience because the application won't be busy doing things not relevant to the current experience. Lifecycle methods also make sure objects are destroyed when they're no longer being used, saving resources. For example, a product catalog might load recommendations right after the page is displayed, so users immediately can get relevant data without unnecessary delays. However, fetching this data from an API can take time, especially with slower networks or larger data sets. To handle this, Blazor enables asynchronous programming techniques so that your application stays responsive during data retrieval. Asynchronous programming enables the app to perform multiple tasks at once, making it more responsive. For instance, when you place an online order, you can continue browsing the site while waiting for the order confirmation to appear. This behavior can keep your app responsive and delight your users. In this video, you learned about the essential components involved in integrating APIs into Blazor applications. By mastering HTTP client, JSON deserialization, lifecycle methods, and asynchronous programming, you're equipping yourself with the tools to transform static applications into responsive and data-driven systems.
APIs, or application programming interfaces, are kind of the backbone of how data gets transferred around the internet. When you have a client app like a mobile app or in your web browser, and you need to fetch data, you need to get data from a remote server, application programming interfaces are the way that it's typically done. And what we're going to do in this screencast is, through a simple app, show how you can use the get command to retrieve data from a remote API. I have a simple Blazor application set up. I used the .NET New Blazor Wasm template to create this application. And then I added a fetch data.razor file to the pages folder in this application. The path here is fetch users. That's the route that we need to browse to when we open the site up. And then at the top of the file, we just have some HTML with some Blazor directives that allow us to interact with the C# code. So we have an if statement that says if the page is loading, show the spinner. So we don't have a message, you just have a spinner that's being shown. If the error message is not empty, if there's a message that we want to display, we're going to display that message back to the user in this application. And then finally, the second else if clause, if the user's variable isn't null, so that's been populated by our C# code, then we're going to display the information that we retrieve back from the API in our application. We have a for each statement here. It's going to retrieve all of the user information and display that in a table format. The last clause we have here is an else clause, and that is essentially saying that if the API call was made, it was made successfully, but there was no data that was returned, we're just going to show no data available to the user, and that just gives the user a better experience. We have our @code directive here, which is where our C# code is, and this is where we're going to do most of the work. And we are going to use the HTTP client in this code. We have http.get from JSON async method, and we're using that HTTP client in order to make that call. At the top of the file, we're injecting the HTTP client and assigning it to the variable HTTP. And now that we've injected that library into our page, we can use the methods that are part of that library. So we inject that at the top of the page, and then we can use it here in our @code directive. So what we're doing here first is creating a list of users, and a user is just a C# object that I've created at the bottom of the page. The class user has an ID, name, email, and address fields that will populate from the API call. Notice that the address field is also an object. So as a part of the address, we can populate street, suite, city, and zip code. And that becomes the type for this address field in our user object. So the first thing we do is we create a list of those user objects. When the API call returns, we're going to get a JSON file with a bunch of data in it, and we'll populate the user objects in that list from that data. We have just a bool message letting us know if the page is loading, and then our error message that we can display if we need to. Then we have a fetch users method that I've created. And notice that this is async. So when we call the fetch user method, that method, if it's been called multiple times, will queue up and it will run in order. So if we call it once, it'll make a call out to the API, wait for the data to return. And if we call that method multiple times, it will just continue to run in turn. You'll notice here that I have a button also in our HTML. When that button is clicked, it calls that fetch users method. So this is how we retrieve data from the API. We click the button calls this fetch users method, and then the method makes the call out to the API. We have a few other variables that we're populating here, kind of manage the call to the API. But the real magic happens at this line inside this try block. Users equal await HTTP get from JSON async. So remember, users is a list. So when this method is called, it's passing in the type list user, so it knows what type of data we should fill when the call comes back from the API. And then we're calling this JSON placeholder.typicode.com/users. And this is just a demo API that you can use to test whether your code works. This is what we're using to retrieve data. And if the data that comes back is in the format of this class that we set up. So we already know that when the data comes back, it's going to have an ID, name, email, and address field, and the address is going to be structured like this. And it's important that you know what the structure of the return data is. And typically the API on the server side has a page that describes what the data return type is so that you can create the classes in the proper way. So when this data comes back, it's going to be of a type user, and then we're going to populate our list using those user objects that come back. If an exception occurs, then it's going to hit the exception block and fill the error message with error fetching data. We're managing our variables here. So after either the try block runs or the catch block runs, then we populate these variables. Is loading will be false, and then we change the state so we know what state the call is in. Let's run this code. So it'll take a moment to build. Then we'll browse to our page. So it's going to land on our landing page. This is just our home page at the route that's at the root of the application, but we can go to our fetch users page to get to the page that we want to see. So you can see we have a title, the users, and then there's our button that we saw, and it's showing no data available because we haven't called out to the API yet. So I'm going to click our button, fetch new users. It goes out to the API and then retrieves those users back and populates the HTML that we saw at the top of the page. So when I click that button, calls the fetch users method and goes out to JSON placeholder, typicode.com/users, and retrieves the data. Now let's see if our try catch block works. I'm going to comment out, first of all, let me stop the application. And I'm going to comment out this line and uncomment this line. This is an endpoint that doesn't exist. This is an invalid endpoint. So when the get from JSON async attempts to make a call to that endpoint, it's going to fail, and it will produce an exception and populate error message. And we should see that error message in our application when we try to fetch the data. So I'm going to rerun the application, and then I'm going to go back to my web page and click fetch new users. Oh, I got to refresh the page. And then when I click fetch new users, it just populated that error message. It says error fetching data. And the message that it gave us is that the response status code does not indicate success 404, which means that it couldn't find the endpoint. The endpoint was not found. That's in our code, error message, error fetching data, and then it produces the exception message. This is very flexible because whatever issue is encountered, whatever exception is encountered, the user will be able to see that exception and provide information to someone who's trying to debug this page. So this is a very simple application that uses this get method to retrieve data from this API and populate a list of user objects so that we can display those user objects to users on our web page.
When an app fails to retrieve critical data, users don't experience the technical problem. They experience an app that just doesn't work. Learning to handle API errors well ensures your Blazor applications remain reliable, polished, and user-friendly even when things go wrong. In this video, we will explain how to handle API errors and manage edge cases gracefully within Blazor applications. Let's start by examining a few error handling techniques. The first technique we will examine is try-catch blocks, which is a foundational technique for managing errors during API calls. A try-catch block is a programming structure that monitors a block of code for errors, or the try, and handles exceptions when they occur, or the catch. Instead of crashing, the block logs the error for debugging and lets you display users a friendly message like, "We're having trouble retrieving your details. Please try again later." For example, if your app needs product details from an API and fails, a try-catch block ensures users aren't left with a blank screen. This approach prevents crashes and makes troubleshooting more straightforward for developers. Another group of error handling techniques are called fallback strategies. Fallback strategies ensure your app remains functional by displaying default or alternative content when the API data isn't available. They act as a safety net, preventing blank screens or error messages from frustrating your users. By implementing fallback strategies, you can provide meaningful, static content or placeholder data, ensuring users still have a seamless experience, even when live data can't be retrieved. For example, if an API fails to load user profile pictures, you can display a default avatar or placeholder image with a message like, "Image not available yet." This approach keeps your app professional and ensures users always know what's happening. Finally, API call retries can address temporary issues and help ensure your Blazor app receives the necessary information. API call retries are a strategy to improve reliability by attempting the same request again when it fails. These retries can be triggered after a short delay or when certain conditions like network instability are detected. By using retries, you give your application more chances to complete API calls successfully, reducing the impact of temporary issues and improving the user experience. For example, when retrieving live weather data, API call retries give the app another chance to fetch the information if a network glitch occurs. This ensures users receive the latest updates without needing to refresh or try again themselves. While retries are crucial for improving reliability, implementing them manually can be time-consuming and error-prone. Retry libraries provide ready-made tools to handle API call retries effectively, simplifying the process. They also save development effort and reduce complexity. To test these techniques, you can simulate API failures by modifying the API endpoint temporarily, disconnecting from the network, or using mock APIs that return error codes. This will help you verify how your app responds to real-world issues. In this video, you learned how to handle API errors and manage edge cases effectively within Blazor applications. Building reliable applications means preparing for the unexpected. By mastering techniques like try-catch blocks, fallback strategies, and retries, you ensure your app continues to serve users, delivering a seamless experience even under challenging conditions. Okay, in this lab, we're building a little weather app in Blazor that we can use to illustrate these API calls. We're actually using an external API called api.weatherapi.com, and I'll explain how to use that in just a minute. But to set up the project, step one, you're just creating a new Blazor app using the template there, .NET new Blazor wasm-o, and the name is weather app. And then you can open it using the method in the answer key, or just go code weather app, and then it'll open up in its own instance, which makes it a little easier to work with if you do that. Either way works. In step two, we're going to set up the first page and the weather fetch component. So to do that, you go into pages, make sure you clicked on pages, and then you click the new button, and then just type weather.razor. I've already got it created, so I'm not going to create a new one, but we've already got that code. And then you're going to paste in the code in the answer key, which is the weather information page, the HTML, and you'll notice that it's at a route called weather, so /weather, which we'll use later when we're testing. Sorry, that was the wrong one. You don't want to create weather.app because that's already in the template. You want to create weatherfetch.razor, and that has a route of weather fetch. The template already has a weather.razor file, so you don't want to use that. This is the one that's in the lab. So then you'll take that code from step two and you'll paste that into the file. So this is what I was referring to earlier. This is something you will need to look at. If you want to test this, in order to use the API, you have to have an API key. And you have to go to weatherapi.com and sign up. They give you a free trial. I think it's 7 or 10 days or whatever to use this key. And then you'll paste in the key. You can see in the template it says your API key. So between the equal sign and the ampersand, you'll need to paste in the key that you get from weatherapi.com. So once you sign up, it's a free account. Once you sign up, you have to log in. And when you log in on that homepage, it'll show you your API key. And you paste that in there, and then you're able to fetch data. So all this page is doing is grabbing data from that API, which illustrates the point of the guided lab. And then it'll fill these classes with the data that it receives and then show it in the page itself here up at the top. So that's step two. And step three is about adding error handling. Now you'll see that the error handling was already in the original code here to do a try-catch block, but that was already in that code you copied and pasted in. So if it's not there, if we end up updating the lab, you'll just have to paste in the new code and make sure you change your API key to the API key that you get from the weather app. And then you can also add at the bottom, if weather is null, then you can just say it's loading. So let's go ahead. I'm going to go ahead and add that. I forgot to put that in. So I'll put that in below here. And that goes inside the uninitialized async. Okay, so that's step three, is to add the error handling and the loading message. Now that it compiles, I actually did a build just to make sure. We'll do .NET run. And it's running on localhost 5144, so I've already got that up on screen, so I'll switch to that window and go to my browser. And you can see that this is just the base app, and now I need to go to that route, which is weather fetch. So once we go there, then it calls out to the API and grabs the weather information, then populates the HTML with what we need. If you'll recall in the app, we were using Phoenix in our route. You can see Phoenix, you can put in any city there, and that should change to the city and pull the data for that city. So that's essentially it. That covers all three steps, and that's how you set that up. JSON responses are crucial for modern web applications, turning raw data into structured, interactive experiences.
To build dynamic apps, you need to know how to process and map this data to your UI. In this video, we will explain how to process JSON responses and map them to Blazor components. Let's begin by exploring the steps for JSON deserialization, starting with data mapping. Data mapping is the process of converting JSON into .NET objects. This process transforms raw JSON data into a structured format, organizing the information into objects with properties. By using data mapping, your application can easily process and interact with data, enabling smooth integration and functionality. For example, if an API sends product details such as names, prices, and categories, data mapping organizes this information into objects with properties like product name, price, and category. This ensures your application can easily use the data. Without data mapping, deserialization wouldn't be able to translate JSON into usable objects. With the data structure planned, the next step is to install the Newtonsoft.json library. The Newtonsoft.json library is a library for working with JSON data in .NET applications. It helps with deserialization, turning JSON into .NET objects, and serialization, turning .NET objects into JSON. This makes it easier to handle data in web apps and APIs. After installing the library, we'll define a data model to ensure your application knows how to handle the data it receives. By defining the data model, you ensure raw JSON data is translated into a format your application can use. Without it, your app wouldn't know how to interpret or organize the data effectively. For instance, in a store app, the data model might include fields like product name, price, and category. This structure ensures product details are consistently stored and ready to display for users. Now that the data model has been defined, we can use it to process JSON data through deserialization. Recall that deserialization is the process of converting JSON strings into objects based on your data model. It's crucial that the JSON structure matches your data model. If the fields don't align, your application might not know how to process the data correctly. Deserialization connects raw JSON in your app's logic by transforming unstructured data into usable structured objects. For example, JSON data containing product names and prices can be deserialized into objects that your app can easily use to display or manipulate. After processing the data, the next step is UI binding, which connects the data to the user interface. User interface binding, or UI binding, connects deserialized data to Blazor components. This process bridges the gap between your processed data and the user interface, making the information both visible and interactive for users. For example, when displaying a user profile, UI binding connects details like the user's name and profile picture to the interface, ensuring the information stays current. Blazor components make this process seamless by instantly reflecting changes in the data, creating a smooth and interactive user experience. The next step is displaying data in the UI once data has been bound to Blazor components. Updates to the data are reflected in real time, making your app feel responsive and dynamic. This step completes the transformation of raw JSON into meaningful experiences, connecting the backend data with the front-end interface to ensure users always have the latest information. In this video, you learned how to process JSON responses and map them to Blazor components. The ability to process and display data is what transforms raw information into a seamless, engaging user experience. In a previous screencast, we created a simple application that makes a call out to an API and retrieves user data from that API. In this screencast, we're going to build on that application by modifying it slightly to show how we can manage state and API data updates in our API calls in a Blazor application. So we have the simple application, again, that retrieves user data from a remote API. That remote API is jsonplaceholder.typico.com/users, and it just retrieves user data that we put into a user object, and we fill a list of user objects with the data that's returned from that API. We have some HTML here at the top that we populate on our web page to show the data that we get back. Now, I made a few modifications to this application to show how we can manage state within the API call. So I've added this cancellation token, which allows us to notify the app if too many requests are being made so that we don't make all the requests at the same time. We have a button on this page. If someone clicks the button too many times, we want to be able to catch that and prevent that call from being made. Now, this async task, the fact that this is the fetch users method is async, means that if a user clicks a button 10 times in a row, 10 tasks will be queued up and make that call to the API 10 times. Many times users will click a button because they don't see an immediate response. And a lot of times we don't want to continue to make calls to the API because that's a strain on resources. A single user clicking a button 10 times isn't a big deal. But if you have 100,000 users clicking that button multiple times, it just continues to make calls over the internet to the API and it can put a strain on the resources. So what we're going to do here is manage the state of our API call and make sure that users aren't allowed to continue to click that button. They can make calls every once in a while, but we don't want them to continue to queue up multiple calls and make those calls to the API. So I've made some modifications to our application where we can manage that. And one way we do that is to create this cancellation token source variable. I'm putting it in the variable named CTS. We're going to be able to manage state that way. We have the same variables we had originally. We have isLoading and state has changed method that will allow us to manage the state. And now we have this cts.cancel method, which will cancel any previous request when fetch users is being called. So if the call has not completed, it will cancel that request and start a new request. And you can see here we're using the cancellation token source method in our CTS variable to manage that process. We also are creating a variable called token, and that's just the CTS token that we've created using our cancellation token source library. I've added a delay in here just to simulate a slow call to the API so that we can see how the cancellation works. This is such a simple app and the call to the API happens so quickly that without that delay, we wouldn't be able to see the cancellation because it makes the call so fast. So I've added just a simple delay here so that we can cancel the request once a new request is made and we can see that working. We have the same call here. We're populating our users variable, our list of users from this API, HTTPS JSON placeholder.typico.com/user, and then we're passing in the token along with that so that we can manage the state of the call to the API. Notice here we have a couple of catch blocks for our try catch statement. The first one is task canceled exception. So if the task is canceled, we're going to take a different action than if there was an exception for any other reason. So this is where we can manage multiple requests. For example, you can imagine a scenario where if a user is really pressing a button many, many times, you can pop up a message that says, previous request is being processed, please wait, or something like that. And then any other exception where an error has actually occurred will produce a different message. In our case, we're just writing out to the console, but you can imagine a scenario where you can do different actions based on the type of exception that was produced. The other thing I've done here is I've added a query string called limit, and this is one that typico.com supports. And I'm just creating a new random number for between 5 and 10. And all I'm doing is telling the API, I want to get back anywhere between 5 and 10 users every time I make this call. And that's just to show that we can produce different data when we make our API calls to show what that looks like. So we have our try catch block with our new task canceled exception, and then our finally block, which is what we had in our previous version of this application, which just manages variables. So let's go ahead and run this. Browse to the application, and then I'm going to browse to our route, fetch users. Now, when I press the button, it should go out and retrieve the data. And you can see we got 5 records back this time. And now I'm going to press the button again. We should get a different number in a moment. Now we've got 8 records. So that's that random variable that I set in the API call. I'm just passing a limit. I want anywhere between 5 and 10 records back. Now I'm going to open up the dev tools so that we can see the error messages that are produced. I'm on my console, and now I'm going to press the button multiple times at once. Notice that I pressed the button 5 or 6 times. It produced 5 instances of previous API call was canceled. And in our application, that's exactly what our message is here. So when I pressed that button too many times, it ended up producing this task canceled exception because the previous call had not completed. Because the previous call had not completed, it's producing that exception previous API call was canceled. If I press the button again, it should get a different amount of users back and not cancel the call. So I can press it too many times. In between 2 seconds, you can see that it produces that exception. By using cancellation token source, we can manage the state of our API calls. And that allows us to make sure that users aren't making too many unnecessary calls to our API. And there's lots of ways that you can manage how that happens and how you message to the user, what to do in those cases. But this allows us to manage state to make sure that our API updates are handled in a reasonable way. In this lab, we're just going to be creating a simple Blazor app and then showing how we can hit an API to retrieve data and then also manage state. In step 1, creating the new Blazor Wasm application, which I've done, dynamic app. I do that from a root folder, and then I switch to the application by doing code space dot and then hitting enter, and that will open up the app in a specific window, its own window like I have here. Step 2, we're creating the user fetch.razor page, which I have up. If you copy and paste the code in, you'll get that. What's important is to make sure that this route is correct, user fetch, so that we can get to the page later. And then we're going to inject HttpClient so that we can use that to fetch the data from the API, which is here. You need to make sure that we have await and then the HTTP call, the get from JSON async method that we'll retrieve from this API. I'm going to show how this works real quick so that we can move on to the next step in a second. So I'm going to go to the page and I'll switch over to that page to show you what it looks like. And then we just go to fetch, user fetch. And that just retrieves all those names from this open source API. So that's how that works. The last step is managing state. And I'm going to stop the application. Control C stops it. In this last step, step 3, we're adding state management, which is a new class. So I can take that class and I can paste it into this Razor file. So I'm going to just paste it below the class user. Now we have a state service class. The lab does not show how to use the state class. So right now this code up here just doesn't use it at all. It doesn't like manage state. This is a service that will help manage state, but it's not implemented in the lab for some reason. But we can easily implement it if we need it to demo it. So I'm just going to add some properties here. And I'm going to replace task on initialize, and this is all in the lab document. I'm going to replace this with a new method. I've added state service so that we have a new object that we can use. We still have our uninitialized async method, and then in that we have state unchanged. And instead of assigning just fetched users and sending that back, we're using state.update users and using that state object to manage the user data that we're getting back from the API. So that's actually how we would use this variable in the real world. And again, I can run that. Now if we go to user fetch, so it still returns all the data, but it's now using that state in order to do so. If we had other pages that wanted to use the same data, the state manager would help us do that. That's how you set up that one. Behind every smooth, responsive app you use is a technique that keeps tasks running without delays, called asynchronous programming. It's fundamental to modern web applications, ensuring efficiency and seamless interactions. In this video, we will describe the basics of asynchronous programming and why it is essential in modern web applications. Let's begin by defining asynchronous programming and understanding more about what it is. Asynchronous programming is a method that allows a program to perform tasks in parallel without blocking or waiting for each task to finish before starting the next one. For example, imagine browsing an online store where product images load as you scroll. Asynchronous programming enables the app to fetch and display the images
while you continue scrolling without freezing or delaying your interaction. Now that you understand what asynchronous programming is, let's explore some of its key concepts. To achieve seamless multitasking in an application, developers use tools like task and await to efficiently manage and coordinate background operations. The task type and await keyword are key components of C#'s asynchronous programming model. They allow the app to perform background operations and display information as soon as it's ready, all while keeping the interface responsive and enabling users to interact with other features. Asynchronous programming goes beyond individual tasks, offering strategies for managing multiple operations simultaneously. Two approaches to achieving this are concurrency and parallelism, each tailored to different multitasking challenges. Concurrency is the ability to manage multiple tasks by allowing them to make progress independently, often by quickly switching between them. While the tasks don't necessarily run at the exact same time, they create the appearance of simultaneous execution. For example, in a customer support system, concurrency allows the system to handle multiple chat conversations by rapidly switching between them. This ensures each user gets timely responses, even if only one process is active at a time. Parallelism, in contrast, involves executing multiple tasks at the same time. This approach is ideal for tasks that can be divided into smaller pieces and processed simultaneously. For example, in data analysis, parallelism splits a large data set into smaller chunks, processes them on multiple processors, and combines the results. This significantly speeds up the overall task. Concurrency and parallelism address different performance needs. Concurrency improves responsiveness in scenarios where efficient task switching is key, while parallelism accelerates tasks by leveraging multiple hardware resources to process operations simultaneously. Both play a crucial role in building better systems. Asynchronous programming ensures applications stay responsive by allowing background tasks to run without disrupting user interactions. For example, when streaming music, the app continues playing songs while you browse playlists or adjust settings. This seamless experience is made possible because tasks like fetching data or loading media run in the background, freeing the app to handle user inputs instantly. Along with responsiveness, asynchronous programming helps applications manage tasks more effectively. For example, messaging apps use asynchronous operations to handle thousands of real-time messages. Concurrency allows the app to switch between the sending, receiving, and syncing messages activities for multiple users. This ensures efficient progress on all tasks. At the same time, parallelism processes multiple messages across different cores, speeding up the delivery and synchronization of data. Finally, asynchronous programming simplifies development by making complex tasks easier to manage. Managing long-running operations like syncing data with a server can be challenging. Asynchronous programming simplifies this process, reducing errors and saving developers time. In this video, you learned about the basics of asynchronous programming and why it is essential in modern web applications. Asynchronous programming transforms how modern apps handle tasks, making them responsive, efficient, and user-friendly.
When you're making API calls in a Blazor application, sometimes things go wrong, and sometimes there's delays when you're making the calls because you're actually going over the internet. Sometimes there's a problem on the receiving side, on the API side. Sometimes there's an issue with your app. We're going to show how you can use asynchronous calls so that it doesn't block the interface while the call is being made to the API. It's happening in the background. And then we're also going to show how you can kind of deal with issues if something goes wrong in your API call. I have a simple Blazor application that we've been using in other screencasts, and it essentially fetches data from an API called typicode.com, and it loads it into an object at the top of our application of this fetchdata.razor file. We have some HTML. There's a button that calls a fetch users method, which is in our code directive here. The fetch user method makes the call to the API and receives a data package in JSON format back from the API. So every time we click this button, it's going to go out and try to fetch that data. Once the data is fetched, it places it in an object, which we've created here in our @code directive. We have a user object that uses an address object, and then that data that comes back in JSON format, we're going to populate into a list of users in this user object. So that's happening when we make the call. And then as that user object gets populated, it will show up in these HTML elements on our web page. I've added a spinner. So when the data is loading, we're simulating it going out to the API. When the data is loading, we're waiting for the API call to return. We'll see a little spinner to show that something's happening instead of a loading message or something else. I've also added the error message in case something goes wrong. In the fetch user method, I want to simulate an error so we can show how to manage that error if something happens. I have a little randomizer here that when I click the button, sometimes it will go out to an actual API, the live API that will return data, and sometimes it will go to this invalid endpoint. When it hits the invalid endpoint, it's going to try to retrieve data, but it can't find the endpoint, so it will produce an error, and it will hit this catch block and cause an exception, and then that will populate the error message so we can see that something's gone wrong, the error was produced. This could be obviously any number of things in a real world scenario. The endpoint could be down, there could be too much internet traffic and it takes too long. So you can imagine a number of exceptions that you would want to show to your user that something has gone wrong and they need to retry. And then we have our other harness logic to make sure that the API works. So the first thing I'm going to do is run the application to show how this works when we actually get some errors and when it completes the way that it's supposed to. So let's run the application. And I'm going to browse to that page. And we have to go to our fetch data route. So there's our button, and we haven't clicked it yet, so we don't have any data. I'm going to click it and see what happens. Okay, so the first call went out and found the data. Click it again, and it hit the appropriate URL. Now this time when I click the button, that randomizer sent it to the invalid endpoint. So we can see we get an error message back, error fetching data, response status code does not indicate success. In other words, that URL endpoint wasn't found, and we can indicate that to our users. So that's how we can use this method to manage issues with our API call. What I might do in a real world scenario is saying there was an issue retrieving the data, try again, and then the user can press the button again. And then at some point, they're going to get a successful call because it goes out and finds the actual API. So let's go back to our application. That's one way to manage issues and asynchronous calls. If there's an issue with the asynchronous call, you want to make sure that you're trapping that and that you're handling it properly. Now, the next thing that we want to do is illustrate how asynchronous calls can be used to process information, but allow the user to interact with the web page. So I'm going to stop the application from running by hitting Control-C, and then I'm going to add this delay. So this is a 2-second delay. It's a simulated delay, but in a real world, some APIs are slower than others. So sometimes there's going to be issues where it takes a while for data to be retrieved, particularly if there's processing that needs to be done on the API side. If you send a complicated query or if the data has to be retrieved from long-term storage, it can take a while for that data to return. So I'm going to simulate that by adding this delay. And when the data is being retrieved, there's a spinner that occurs. The spinner happens when the data is loading. We should see that spinner on screen, and then it will complete the API call and the spinner will go away. So I'm going to run the application again. And I'm going to go back and refresh the page. Now we'll fetch the data, and you can see our spinner shows up for 2 seconds, and then it actually completes the call. Just a good way to enable users to continue to interact with the application when something's happening. It just helps them to know that something's going on, that it's working. Now you notice because it's an async call, when I press the button and the spinner is on screen, I can actually still interact with the app. So you can see I was able to go to that ASP.NET About page, even though it was still trying to retrieve the data from the API call. That's because this is an async call. So the async call allows us to continue to interact with the page, even though it's still doing work trying to retrieve that data. Also notice that when I went back to the page, the data had been retrieved or the error occurred because it was working in the background, even though I was able to interact with the web page. So that's an important feature for using API calls. Using that async approach allows your application to remain responsive, even though there's work being done to retrieve data. So using these methods, you can continue to build your app in a responsive, manageable way and make an application that really does delight your users. Okay, in this lab is a very simple lab. We just have a basic Blazor application. So in step one, setting that Blazor application up, what I've done, we've got the async API app open in VS Code. So you run the .NET new Blazor Wasm that creates the new application in a folder. You can switch that folder using cd space and then the folder name, and then use code dot to open it up in its own instance, which I have here. In step two, we have fetch users.razor, which is in the pages folder, and it's at the fetch users route endpoint. So we set that up. So make sure it's fetch users and that we're using HttpClient. And then we're still using that same JSON placeholder typico.com users endpoint, the API that we're retrieving data from. The key here for the learner is to use the async methods for that. So we have a private async task. So the task needs to be there. That's the item 6, I think. Yep. And then after the await, we're going to use http.get from JSON async. So these are the async calls that we're pointing out in the lab the learner needs to have in place. So with the await keyword before the async method call, or it will fail. And that's really all there is to this lab. And then you can run it if you need to make sure it works. But I verified that the code works and it's very simple. So there should be no issues here. Efficient applications aren't just faster. They provide a seamless experience that keeps users engaged. Optimizing your app's communication with the server can transform performance and reliability, ensuring your Blazor application stands out. In this video, we will explain strategies for optimizing API calls to improve the performance of Blazor applications. Let's begin by exploring some common performance optimization strategies. Caching API responses is a straightforward strategy to improve your app's performance by reducing unnecessary work for the server. Caching API responses refers to temporarily storing the data returned by an API to reduce the need for repeated requests. By keeping a local copy of the responses, your application can quickly retrieve the data without making another call to the server. This approach minimizes redundant requests, improves performance, and reduces server load, all while providing faster and more responsive experiences for your users. To start with caching, you must first identify which data to store locally. Identify data that users often request, such as product lists, and store locally. For example, caching weather data avoids repeatedly downloading the same forecast. Once the data is stored, it's important to define how often it should be refreshed. You can set rules for when cached data should be updated. For example, update live sports scores every minute, but keep product categories cached for an entire session. Blazor applications can implement caching using shared services or local storage. Caching reduces redundant requests, but pagination is helpful in managing large datasets efficiently. Pagination is the process of dividing large datasets into smaller, manageable chunks. By only transferring a limited number of items per request, pagination prevents your app from loading excessive amounts of data all at once. This approach significantly improves loading times, reduces bandwidth usage, and enhances the overall user experience by presenting data in a more organized and digestible format. To implement this strategy, display only part of the data at a time, like 10 items per page. For example, load 10 product reviews initially with the option to load more as needed. Pagination can be implemented in Blazor using data grids or lists that request paginated data from the API. Another way to implement pagination is to allow users to navigate additional data by using buttons like Next or Previous, or by scrolling. For example, in a photo gallery, users can select Next to access the following set of images. Pagination manages large datasets, but you can also implement a rate limiting strategy
due to frequent API requests, which can lead to server strain. Rate limiting is a technique used to control the frequency of API requests. It sets limits on how many requests a client can make within a specific time frame. By regulating request rates, rate limiting helps prevent server overload, ensuring the system remains stable and responsive. It also promotes fair usage, making sure that all users have equal access to the API without any one client monopolizing resources. To implement this strategy, reduce request frequency and make requests only when necessary by combining or delaying them. For example, load profile images in batches instead of retrieving them one at a time. You can also implement rate limiting, making sure they stay within API limits by monitoring the API's provider's request limits and adjusting them accordingly. For example, if the API allows 100 requests per minute, introduce delays or provide a message if the limit is reached, and ask the user to try again later. In this video, you learned about the strategies for optimizing API calls to improve performance of Blazor applications. These strategies complement each other to effectively manage redundant calls, large datasets, and server overload.
When you're working with APIs, security and maintainability are really important. You want to make sure that you're passing data to an API securely and that you're receiving the data back in a secure way. So in this screencast, we're going to look at two ways that you can implement security and make your API calls a little bit easier to maintain. I have this simple Blazor app that I've created using the .NET new Blazor Wasm template. I have a fetchdata.razor page that I've created that I'm going to use to make my API calls. And I've created two other pages. I've got a error logging service that I'm going to use to log issues that happen with the API call. That's going to help us to make our API calls and our application that uses API calls a little bit easier to maintain. And then I've got a token service that I'm going to use to generate a token so I can securely send and receive data to a remote API. So let's walk through this. I've got some HTML here at the top of the page just to show the token to the user and then the API message that's received back when we make that remote API call. And then I have the @code directive, which is going to outline all the C# code that we have and use for our API call. You can see I'm doing all the work here in this onInitialized async method. That just runs when the page loads. So whatever happens when the page loads, we don't have any buttons or anything. We're just going to generate the token, make the API calls, and get the data back. The first thing that's happening in this method is that we're generating a token. Tokens are used to send data securely over the internet. So instead of sending like an email and password, you can generate a token out of the email and password. And then the receiving API can decrypt the token and get the information out of the token that we need. So let's take a look at this token service. All it's doing is returning a single string. It's using fake data, fake email and password to generate that. So we're using HttpClient for this token service, again, just as a demonstration. And I'm serializing JSON data, which is an email field and a password field. Again, this is fake data calling demo API that will generate a token out of this data. So we have the email address and the password. We don't want to send that in the query string. We don't want to send that in raw text because someone can snatch that text and read it. So we're going to use this service, this recres.in service. We're going to send that data to that service to get a token back. And then when we get that token back, we can use that token against another API to securely send that data. So you can imagine that instead of this demo website, we would have our own website that we can use internally to generate the token. And then when we want to go outside of the application, we'll send that token instead of the email and password in plain text. So that's what's happening here. So we're going to call out to the service. It's going to generate the token, send the token back to us. We're going to be able to read that token and use it in our API call. So when we go back to our page, we grab the token from our service that we've created, and we'll write that up to the screen and to the console. And then we're going to use HttpClient again and make a call to jsonplaceholder.typicode.com, which is again a demo site that we can use to test APIs. And we're going to attach the token that we created to the header of our API call. And that's what this client.defaultRequestHeaders.authorization is doing. It's just taking that token. It's called a bearer token. It's attaching it to the header of the API call. We define what API response is, which is just getting the string that we need. We're going to be attaching that because we're using the client object. We're attaching that token to the get string async call. It's going to be a part of the header of that call. So if someone grabs that request, they're going to see the token, which is going to be essentially meaningless to them unless they can decode it. They're going to grab the token, but they won't see the username and password. And then in the rest of this, we're simply writing back out the JSON that we get back from the API call. So we'll run this application. Our application is running. I'm going to go ahead and open that up in our browser. We're going to have to browse to our route, which is fetch data. And when we open this page, it's going to generate that token and then make the API call. So here's what the token looks like. It took that email and password and generated this ambiguous string of characters. And the token is decrypted or understood on the receiving side of the API. It's using the same method to decrypt it as we use to encrypt the email and password. So it knows how to use it. And then we pass that information to the API. It decrypts it, logs the user in, and then provides data back. You can see this is just fake data, but the point is that the data came back. It was able to log the user in, grab the data it needed, and return a response back to the calling method. So back in our application, we can see that the API call worked because we did pass that token. Now this JSON placeholder.typico.com doesn't actually need a login, but we can pass the token in to show how it would work if we were in a real world situation. The last thing we want to do is be able to handle errors to make our API calls and our applications better managed. So what we've done here is integrated an error logging service so that we can capture any issues that happen. The error logging service is very simple. It just writes out to the console if there was an error. We pass that error into the log error method. You can imagine though here we could do a lot of other work. We could send an email if something goes wrong. We could retry the API call if the network was busy for some reason. So we can capture whatever error occurred, and then we could do a bunch of work in this method or a number of methods if we want to. We call that in our fetch data razor file. So we have the API call in a try catch block. The try block is going to try to send that message to the API. And then if something goes wrong, it catches it and creates an exception. And then we send that exception message to the log error service, which at this point is just writing something to the console. So it's not doing much, but it does allow us to better manage our application when we do have issues. So I'm going to stop the application and I'm going to send the API call to an endpoint that doesn't exist. So it's going to essentially fail. And I'll show you how this works in the debugger. So then debug this application and we should get a breakpoint here and it should stop when the error occurs. So we'll go back to fetch data. So we hit our breakpoint. It's now going to call the log error service, the error logging service and the log error method. I also put a breakpoint in the log error method to show you how this works. So now it's inside the error logging service, and then we can do the work that we need to do here. So I'll continue to run the application. Let's go back to the browser and we can look in our console in DevTools. Status code did not indicate its success, and it gives us a 404 and it tells us what happened in that error. This is what we're seeing based on that service that we created, the token service. And again, we can do a number of things here in order to retry or provide a message to the user. This screencast shows how you can use various tools in Blazor applications to make your application a little bit more robust. You can make the application secure by using tokens, and then you can use a logging system to better respond to issues and to help you and your users know what's going on when you're making these API calls.
In this module, you've learned how to integrate APIs into your Blazor projects, make and handle API calls, implement asynchronous programming, and follow best practices for API consumption. By the end, you gain the skills to create dynamic, responsive applications powered by robust API integrations. We began by defining the fundamentals of API consumption in Blazor, establishing a clear understanding of how APIs enable dynamic, data-driven applications. This lesson covered the basic principles of working with APIs in Blazor, ensuring you understood the key role APIs play in modern web development. By laying this foundation, you became better prepared to connect your applications to external data sources and unlock their full potential. Next, we explored how to make API calls in Blazor, focusing on techniques to fetch and display external data effectively. You learned how to initiate API requests directly from your Blazor applications using HTTP clients and other tools. These skills were essential for creating applications that retrieved and displayed real-time data from external services, enhancing interactivity and user engagement. Then we examined how to handle API responses in Blazor, learning to process and display data in ways that enhance user interaction and application performance. This lesson taught you how to parse and utilize API responses, ensuring that raw data was transformed into meaningful, user-friendly information. Understanding how to handle responses was critical for maintaining a seamless user experience and building reliable features. After that, we delved into asynchronous programming in Blazor, mastering techniques that ensured your applications remained responsive while managing API interactions. You explored the concept of asynchronous programming and how it applies to Blazor applications, particularly when working with APIs. These techniques enable tasks like data retrieval without freezing the user interface, improving both functionality and performance. Finally, we discussed best practices for API integration in Blazor, covering key strategies for optimizing performance, enhancing security, and ensuring maintainability. This lesson provided practical guidelines for making your API integrations robust and efficient, from error handling to secure data transmission. By following these best practices, you built Blazor applications that are reliable, scalable, and ready for real-world use cases. Congratulations on completing consuming APIs in Blazor applications. By mastering the essential skills to integrate APIs seamlessly into your Blazor projects, you've equipped yourself to create dynamic, responsive applications that leverage the power of APIs to deliver real-time functionality and robust data handling. With these skills, you're ready to unlock the full potential of API integration in Blazor and create applications that stand out for their interactivity, reliability, and scalability. Great work, and keep building amazing applications. Welcome to State Management and Client-Server Communication, a critical module in the Full Stack Integration course. In this module, you'll explore the essential concepts and techniques that enable seamless interactions between the client and server. By mastering these topics, you will gain the ability to manage state effectively and implement effective communication strategies, ensuring your applications are robust, responsive, and scalable. We will begin by exploring state management in full-stack applications. Understanding state, the data that drives your application's behavior, is foundational for creating dynamic interactive user experiences. This lesson will help you appreciate the significance of state management and how it underpins every aspect of modern application development. Next, we'll dive into client-side state management. You'll explore techniques such as using local state, global state management libraries, and caching to ensure your application responds swiftly to user interactions. Mastering these strategies will empower you to build user-friendly applications with efficient performance. In the next lesson, we'll shift our focus to server-side state management. You'll learn how to maintain consistency and reliability across distributed systems by using sessions, database management, and server-side caching. In this lesson, we'll shift our focus to server-side state management. You'll learn how to maintain consistency and reliability across distributed systems by using sessions, database management, and server-side caching. This knowledge will be critical for building applications that scale gracefully and handle complex workflows. We'll then explore real-time communication techniques, including WebSockets and server-sent events. Real-time capabilities are increasingly essential in modern applications for features like live chats, notifications, and collaborative tools. This lesson will equip you to implement real-time solutions that keep your application engaging and interactive. Finally, we'll conclude with best practices for state management. You'll learn how to choose the right tools and strategies for your project, avoid common pitfalls, and maintain code that is clean, scalable, and maintainable. These principles will set you up for success in managing state across diverse application requirements. State management and client-server communication are cornerstones of full-stack development. By the end of this module, you'll have the skills to design applications that are efficient, responsive, and capable of scaling to meet user demands. Let's get started on this exciting journey into state management and client-server communication. Applications that lose track of your shopping cart, log you out unexpectedly, or reset your filters can be frustrating to use. State management prevents these issues by allowing applications to adapt, remember, and respond consistently to user interactions, forming the foundation of seamless user experiences. In this video, we'll define what state management is and how it influences application behavior over time within full-stack systems. To start, let's define state management. State management refers to the way an application handles the data, or state, that changes over time, ensuring that different parts of the app have access to the same information and stay synchronized. Recall that state is a snapshot of all the data at a specific point in time that an application needs to function. State management is like organizing a shared whiteboard in an office. If everyone writes, erases, or updates it without coordination, it becomes chaotic. But with clear rules, state management, everyone has access to the same up-to-date information. Now let's explore some key concepts of state management. Before an application can adapt and respond to user interactions, it needs to know the state of the application. The concept of a state is a fundamental concept in building responsive systems. State refers to the data or the current condition that an application is in at any given moment. It represents the current status of variables, data, or user interface components. Think of state as the memory of an application. It allows the system to keep track of what you've done and adjusts its behavior accordingly. For example, when filling out a multi-step form, the app remembers the details you've entered in earlier steps so you don't have to start over. State is used to track different kinds of information, and depending on what kind of data you need to manage, it's organized into 3 types: local, session, and global. Let's review each one, starting with local state. Local state is data that is confined to specific parts of an application, typically within a single component or small group of related components. This state is essential for powering front-end features like forms, where a component might store input values in its local state, like the text entered in a field or whether a checkbox is checked. For example, consider a drop-down menu that only needs to know whether it's open or closed. This type of local state is lightweight, focused, and doesn't impact other parts of the application. This ensures smooth and efficient interactions. The next type of state we need to explore is session state. Session state is data that is stored and persists for the duration of a user's session with an application or website. It allows the application to remember user activities like saving progress on a form across multiple pages. This ensures a seamless and consistent experience as the user navigates through the site. For example, session state would track items in a shopping cart. It lasts only for the session and is cleared when you leave the site. On some websites, the session may also be cleared if you remain inactive for a certain period of time, typically 20 to 30 minutes, depending on the server's configuration. The last type of state we will explore is global state. Global state is data that needs to be accessible across multiple parts or components of the application. It ensures that important data like a user's login status remains consistent and available regardless of where the user is within the application. For example, global state keeps you logged in as you navigate between different pages, ensuring a consistent and seamless user experience. Now that we've covered the concepts and tools for state management, let's examine how they work together in a real-world example.
Think about an e-commerce platform you've used. It relies on all types of state to create a smooth shopping experience. For example, local state manages small tasks, like toggling between product images when you hover over them. Meanwhile, session state keeps track of items in your shopping cart as you browse across different pages. Finally, global state ensures you stay logged in and your preferences are remembered throughout the site. State management like this ensures applications remain responsive, intuitive, and enjoyable for users. In this video, you learned about what state management is and how it influences application behavior over time within full-stack systems. State management is the foundation of every modern application, ensuring they can adapt and remain consistent over time. Behind every smooth interaction in your favorite app is a system ensuring your data stays consistent, no matter how many times you click, return, or pause. This is the power of state management, an essential element of reliable digital experiences. In this video, we'll explain how state management ensures consistent user experience across interactions in full-stack applications. To begin, remember that state management refers to the way an application handles data, or state, that changes over time. This ensures that different parts of the app have access to the same information and stay synchronized. The app will remain consistent by maintaining a single source of truth for data, allowing all components to access and update it predictably. Let's explore the key features of state management that ensure this consistent user experience, starting with state-driven user interface, or UI, updates. State-driven UI updates ensure that the user interface responds instantly to changes. For example, when you add an item to your cart, the cart icon updates immediately, giving you real-time feedback that confirms your action was successful. This seamless interaction creates responsive and user-friendly experiences, keeping users engaged and informed. Next, let's explore user session continuity, a feature that keeps track of users across multiple actions during a single session. User session continuity ensures that your progress is maintained as you navigate the site. For example, after adding items to your cart, they remain there until you complete your purchase, even if you visit other web pages. Next is data persistence, a feature that temporarily or permanently saves information. For example, when you mark an item as favorite in a shopping app, data persistence ensures your choice is saved. Even if you switch to another device or revisit the app later, your favorites will still be there, creating a seamless and personalized experience. Finally, apps have error handling, which prevent problems when the app's data becomes out of sync. It can also attempt to recover by reloading the cart data or offering an alternative solution. This process ensures the app remains functional and avoids unnecessary frustration for the user. Now that we've examined state management's key features, let's explore an example of how they come together in an online shopping platform. Imagine a platform that provides a seamless experience by instantly updating a cart when users add items, state-driven user interface, and keeping their cart intact during the browsing session continuity. The platform ensures that favorites and preferences are saved and accessible across devices, data persistence, and helps users recover gracefully from issues like failed checkouts by providing clear feedback and potential recovery options, error handling. Together, these features create a reliable, user-friendly shopping experience that boosts customer satisfaction and trust. In this video, you learned how state management ensures consistent user experiences across interactions in full-stack applications. State management turns fragmented data into cohesive, seamless experiences, ensuring apps remain intuitive and reliable. Every time a website remembers your preferences or keeps you logged in, it's using client-side storage tools to manage data directly in your browser. Understanding these tools will enable you to create smoother, more personalized web experiences. In this video, we'll identify the client-side storage mechanisms available for managing state in front-end applications. Let's begin by exploring common client-side storage mechanisms, starting with local storage, a mechanism for saving data persistently in the browser. Local storage refers to data that is stored persistently in the user's browser and remains available until it is explicitly removed by the user or the application. For example, imagine you visit a website and switch to dark mode to change its appearance. Local storage saves this preference, so when you return later, it remembers your choice because the data stays stored in your browser even after you close it. Now that we've explored local storage, we'll move to session storage, a tool for temporarily storing data. Session storage is data that is stored in the browser but is automatically cleared as soon as the browser tab is closed. Sometimes it can complement database systems by holding information like session ID. This session ID allows applications to retrieve user authentication details or other necessary data, creating a smooth interaction between the client and the database. For example, when using a multi-step form on a website, session storage keeps your progress intact as you navigate between steps. However, once the session ends, the data is cleared, making it ideal for temporary tasks that don't need to persist beyond the current browsing session. Next, we'll examine cookies, which handle data for personalization and tracking across session and devices. Cookies are small pieces of data stored by the browser. They are commonly used to track user behavior or personalize the user experience on a website. They are widely used in a web development to maintain state between the client or browser and the server. Consider how some websites keep you logged in or remember your preferred language across devices. Cookies make this possible by storing small amounts of data that websites can access at any time. Now let's explore how local storage, session storage, and cookies work together in a real-world example. An online shopping platform might use local storage to save user preferences like dark mode, session storage to temporarily store data like the items in a shopping cart during a browsing session, and cookies to store session identifiers, enabling personalization across devices. Together, these tools create a seamless and personalized shopping experience. In this video, you learned about client-side storage mechanisms available for maintaining state in front-end applications. With client-side storage, you can build web applications that feel responsive, personalized, and user-friendly. Being able to save state between sessions and even between application launches in a Blazor app is an important part of developing an application that has staying power and creates a better user experience. In this screencast, we're going to look at two different types of storage, local storage and session storage. Local storage will allow you to save user information between the app loads, and session storage will allow you to save user information between sessions. So we're going to look at each of these in turn. I have a Blazor application here with a couple of pages that will illustrate both of these types of storage. I've actually added these services to our Blazor application. So you can see here at the top of program.cs, I'm using Blazor ed.local storage and Blazor ed.session storage. I added those as using statements so that I can use the libraries. And then I'm adding it to my builder services to make sure that I can use these libraries elsewhere in my application. The first thing I want to illustrate is how to use local storage. So local storage will actually save data to the user's local machine. And so if the application restarts, it'll read from that storage library and be able to return that data back to the user, even if they close down their browser or the application. We have a home.razor page that I've updated. You can see that I've added both local storage and session storage to this page. For this illustration, we actually only need local storage, but I've added both just to illustrate how it can be done. We're injecting these libraries into the page at the top of the page below the HTML. The HTML is just very simple buttons. We have a toggle theme, which will allow us to switch between changing a variable between light and dark. So we can show how that data is persisted between application launches. And then we have the clear storage, which will just remove all the data from the user's local storage and start over. And then in our toggle theme, we're just switching that variable, that theme variable, from string light to string dark. In a real world application, you might persist actual settings of an app or some other type of data that's more meaningful. Here, we're just setting this string variable theme to a different string and show how we can persist that. And then when the application loads, we're going to actually check to see if the local storage user theme has any data in it. If it doesn't, we're going to populate our string with light. Otherwise, we'll populate it with whatever is in the storage. And then the clear storage method is the button that is the method that's associated with the clear storage button. Here, clear all storage up at the top. It uses that clear async method to remove any data that's in local storage. And I have session storage here as well. So it's a very simple page, but I'll show you how this works. We'll run the application and I'll browse to the page. And since it's our own page, we can just go directly to the page. So there we have our theme switcher. So it defaults to light because user storage was empty. So I'll toggle the theme and it will turn to dark. Now I can refresh the page, the session, and when I come back, it will still be dark, but I'll close down my browser and then I'll come back to that page and you'll notice that it retained the fact that it was dark theme. And it did that because it was saved to the local machine here. When the page loaded, it retrieved that data on initialized sync. It retrieved the data from the user theme storage library, retrieved whatever it had, and in this case, it was dark. Now I can clear all the storage, and then when I hit refresh, it'll return to light because I've cleared that storage out, and our code says that it should always default to the light theme. So that's one way to persist data, and again, that persists between application restarts. Another type is session storage that will just retain the information while the session is active, and that means while the browser page is open. As soon as I close the browser page, the data will be erased. And in here, I have a simple page that it's a shopping cart where you can add an item, and when I click add, it will add the item to session storage using this session storage.setItemAsync method. It will add it to this cart object, which will store the data. It will add any item that I put in my input element here in the shopping cart. What this code will also do is just list any items I have in my cart as I add them. When I refresh the page, on initialized sync will run. It's an async task, and it will get any items from session storage in the cart object that we've created. If the cart object exists for the session, it will retrieve the items in that cart. Otherwise, it will just list an empty string. So we'll go ahead and run this now. We've actually got the app running, so I'm just going to browse to the cart page. So I have my shopping cart. I'm going to add an item. So it shows that I have one item in my shopping cart now. And if I refresh the page, that item should remain. And I'll add a second item and refresh the page. And between the sessions, it will retain that data. Now, if I close the browser down and then go back to my cart, you'll see that the information is gone because we're between sessions now and it doesn't know what to do. It doesn't save that data, it doesn't persist that data. We would have to use local storage for that type of behavior. So those are two types of ways in a Blazor application that you can persist data for the user. You can either persist it to the local machine where it will retain between application restarts, or you can just save it in session so that the data will retain while the user is still on that page or as the app open. In this lab, you'll learn to implement client-side state management techniques in a Blazor WebAssembly application using local storage, session storage, and clearing storage programmatically. In step one, you're just setting up a new Blazor application using the Blazor WASM template. And you're going to call your application client state app. And then you're going to move to the client state app directory and then run the application. In step two, we're going to implement local storage, and we're going to go to the page home.razor to do that. And in that page, you're going to inject the local storage library, the Blazor ed.localstorage.ilocalStorage service. And that service will give access to the application to store variables and information locally. And then in the act code directive, you're going to actually take advantage of that library. And so you'll have a line await local storage, and you're going to set the item to the user theme, it's just a name we're going to give it for the local storage. So you're going to use await local storage.set item async. The user theme is the name we give it, and then we're going to set it to the variable, whatever is in the variable theme. So what this is going to do is when the theme is toggled, it will save the whatever the value of theme is to local storage. And then if the app shuts down and restarts, it can pull that value from local storage so it can reuse it. And then when the task is initialized on the override async task on initialized async, it's going to populate the theme variable with whatever is in that variable user theme. So if there's a value, it will populate it with that value. Otherwise, it'll populate it with the value light. So in this scenario, it allows us to save the value from local storage and retrieve it out of local storage. Now in step 3, you're going to use session storage, and for that we'll move to cart.razor. And you can see here we are injecting our session storage library called session storage, and that will allow us to use that library throughout this code. We're going to call our page cart, and that's the route that we'll use to get to the page when we launch the application. And then we're going to inject the session storage value into the application. In the @code directive, in the add-item method, we're going to create a session storage variable called cart, and we're going to fill that session storage variable with cart items. Session storage allows you to retain information while the session is still active. So as long as the browser page is not closed, that data will remain active even if you refresh. Once the browser page is closed, session storage is deleted. So we're going to populate the cart variable in session storage with whatever is in cart items. And similar to local storage, when we start up the app on initialized async, we're going to also pull from the cart variable. So if the cart variable exists in session storage, we'll populate it with whatever's in there. Otherwise, we'll just create a new list of string variables that we can use to store whatever's in the cart. Similar to local storage, the session storage will allow us to add items to it and then retrieve items from it if it's populated with any values. Every time you shop online or use your favorite app, the smooth experience of remembering who you are and what you did is thanks to server-side state management. This technology ensures your interactions stay consistent and personalized, even as you navigate between pages or return after time away. In this video, we'll describe key server-side state management techniques used to maintain user state across sessions. Let's start by exploring some common server-side state management techniques, starting with session management. Session management keeps track of a user's actions on a website by storing session data securely on the server. When you log into an online store and add items to your cart, session management ensures your activity is linked to your account through a unique session ID. This allows the store to keep your cart intact while browsing different pages. Without session management, your selections could be lost as you navigate through the site, leading to a frustrating experience. Servers employ stateful sessions to manage state properly. This technology enables servers to remember user interactions to maintain continuity. Let's examine what makes stateful sessions unique. Stateful sessions retain user information across interactions, allowing servers to maintain continuity throughout a session. For example, when you log into a social media app, it keeps you logged in and delivers a personalized experience by remembering your account details throughout your session. While stateful systems retain memory between interactions, stateless sessions manage each request independently. Stateless sessions are systems where each request is treated as independent without memory of previous interactions. For example, when you check the weather online, your server processes your request, retrieves the relevant data, and sends it back. However, it doesn't retain any information about you after the response is delivered. While this stateless interaction works well for simple requests like checking the weather, more complex interactions require servers to manage a user state across multiple requests. Managing user state is achieved through 3 key techniques. First, servers assign each user a unique session ID, often stored in a cookie. This ID acts as a reference, linking the user to their data stored on the server. Think of it like receiving a numbered token at a coat check. The token doesn't contain your coat, but helps the attendant locate it. Similarly, a session ID lets the server keep your shopping cart intact as you navigate between pages, ensuring a seamless experience. Additionally, session cookies store references to session data, enabling the server to confirm your identity without exposing sensitive information directly in the browser. Think of a session cookie as a digital key that says, "This is user number 123. The server uses this key to verify your login and maintain your session securely, ensuring that the key itself can't be tampered with or read by unauthorized parties. Finally, because session cookies are often temporary and are deleted when you close your browser, servers use databases to store session information for data that needs to persist longer. For example, a wish list on an e-commerce site is saved in a database, so it's available even after you log out. This kind of persistence ensures a seamless and consistent user experience. A final server-side state technique is caching. Caching temporarily stores frequently accessed data to improve performance and reduce load on the server. For example, news headlines can be cached, so the server can deliver them quickly without repeatedly querying the database. This reduces server workload and significantly improves performance. Together, these techniques provide a seamless and efficient application experience, enhancing usability and performance. In this video, you learned about key server-side state management techniques used to maintain user state across sessions. With all these techniques working together, you can create seamless, efficient, and intuitive user experiences, delivering consistency that keeps users engaged and coming back. When you're working with Blazor apps, sometimes you need to save user data on the client machine, but other times you want to actually save that user data to the server so that users can actually get their data on their mobile phone as well as their desktop and in an application, and it all syncs up. So using session storage and using a cache service, you can actually retain data on the server side and maintain that data on the server side without having to rely on client-side caching or client-side session storage. I'm going to illustrate how this works, server-side based caching and server-side based session storage. I'll do that in a Blazor application. I've created a simple Blazor application using the Blazor template. So we just have a very fundamental and rudimentary application here. I've actually built out 2 pages, one called fetchData.Razor and one called counter.Razor. And I'll illustrate both types of storage using each of these pages. So the first thing I've done is I've created a cache service class, and this cache service class is just an in-memory storage. So in a real-world application, you might want to save data to a database or to disk. Here, we're just saving it in memory for the point of illustration. But this can run on the server, this service, and you can store the data in a database tied to a user ID or an application ID. But we're storing it in memory here just to show how this can actually create a cache that the client side can then use to retrieve data. So all this is doing is creating a read-only variable called _cache. It's using this caching.memory library, a Microsoft extensions library, and it's using the iMemory cache object to create that cache. So the .NET framework will handle a lot of this caching logic for you, so you don't have to write it. You just use the iMemory cache type with a variable, and then you can leverage the power of the .NET framework to do a lot of the heavy lifting for you. And then we have a method called cache service, which essentially sets the _cache variable to whatever the cache is that we pass in, which is also an iMemory cache type. So we pass in some data in that cache variable, and then set our read-only variable _cache to whatever that value is. And then we have a get or create method as well, which takes in a create item variable, and the cache will either get the item or create the item based on what is needed from our application. So this cache service is very simple, but it does illustrate how we can store data on the server side using this caching.memory library that Microsoft provides. Now I'll go to my fetchdata.razor page, which is very, very simple. It's a fake weather information, weather temperature page. And all it's doing here is providing in a paragraph tag, whatever's in the weather data variable. And the weather data variable is set in this oninitialized async method, which runs when the page loads. And the weather data variable is being set by this cache service. So again, we're injecting the cache service, which we created earlier, into our page, and then we're going to use the getter create method that I showed previously, and we're passing in a weather data object, and we're setting it to this data. Now all I've done here is I've created a new random number between 1 and 10, and the temperature will display based on whatever that random number is. Now what's interesting here in terms of the cache is that the entry is setting a cache time. So what that means is that the data that we're setting in this variable will remain in the cache for whatever time we set. And for right now, we're setting it to just 5 seconds. So you can imagine a real world app where the weather is updated and this service will provide weather updates, but you only want that weather to be updated every 15 minutes or every 10 minutes, whatever is appropriate for that application. So instead of continually making calls to a server, you can see here I have replaced with real fetch logic. If we were calling out to another API where we wanted to get the weather information, this cache will only call out to that API when the time span has elapsed. Otherwise, the data that we previously retrieved will stay in that cache. So we're setting the time to 5 seconds so I can illustrate it in the application. But you can imagine that we could set this to a longer time frame and only call out to that API only when that cache is expired. So we're going to use the data from the cache unless the cache is expired, and then we make our call, or in this case, we're going to get a new random number when we run the application. So I'm going to run this now and show how this cache works. Application is running. I'm going to now browse to the website and go to the fetch page. You can see we have our temperature of 4. So when we refresh the page, it's either going to pull from the cache or it's going to get a new number. Now, we've only set it for 5 seconds, so it's been 5 seconds since we loaded the page. So we should get a new number, a new random number. I keep clicking refresh, but you'll notice the number doesn't change because it's pulling that 5 from the cache rather than generating a new number, or in a real world scenario, going out to an API and getting weather data. Now that 5 seconds have passed, I'll click the refresh again and it'll give us a new number. So that's using that cache to store the data. When the cache expires, after whatever time we set, then we can generate a new number based on it. So that's one way to store data, store information, and that can prevent server overloads and making too many API calls when you're working with an application. So now we're going to go back to another page. We're going to go to our counter page, and I'm going to show you how to use session storage to retain information between sessions. So this is a very simple page as well. It just has a button called Click Me. It goes to this increment count method that will just update the counter inc variable by 1 each time I click the button. But notice also that it's saving the information, the counter inc variable, it's saving it to session storage, which is a type of storage in .NET that saves the information as long as the browser window is open. So if the user does not close the browser window or the application window, then the data will be retained. As soon as the browser window closes, the data is erased. So this session storage is using this Blazor ed session storage.isession storage service. And so it's all built into the .NET framework. So you just need to call the session storage set item async, give it a name. It can be any name that you like, and then save the variable to that storage. Notice that when we load the page, if that session storage variable counter inc is populated, it will pull the data from that storage. Otherwise, it will create new data or get new data. So now I'm going to go back to my page and I'm going to click on the counter item and I'm going to click the button and it'll increase to 6. When I refresh the page, it goes to 0. And that's because I'm essentially running a client side page in a server application, but the data will still be retained. So when I click the button again, it'll start at 7 because that data was retained in the session storage. So I'm going to refresh. It should start with 13 because it picks up that data from the session storage and increments it by 1. Now, if I close the browser and then I go back to that page, you can see it starts at 0. When I click, it'll start at 1 again because that session storage was then deleted when I close the page or the session. So those are 2 ways in Blazor that you can retain information both between sessions and on the server when you're trying to manage how data is captured, saved, and then returned to the user. In this lab, we're going to apply server-side state management strategies, including session handling and caching within a full stack application. So in step 1, you're creating the application. We're going to create a Blazor app called Blazor Server App. We're using just the regular Blazor template to do this. And then you're going to switch to the Blazor Server App folder using cd Blazor Server App and then run the application just to test and see if it runs. The next step is configuring session handling. So you're going to configure middleware and program.cs. And we're just going to use a timer here for setting the idle timeout in the options for our session. And in the first line option idle timeout, you're going to set the time span, and we're going to use from minutes. We're going to set the time to 30 minutes. This will allow the session to remain active for 30 minutes. After that, the session will expire. And then we're going to set the cookie to HTTP only for security reasons, and we're going to set that property to true. And that's how you're going to set up your session for this application. The next thing you're going to do is set up a cache service, and this is going to allow data to be cached or saved on the server side so that it can be reused. So if multiple clients request the same information, it will come from the cache instead of having to read it from a database or go to an API, only for a limited time. In order to set up the cache service, you're going to set up a read-only variable using the iMemory cache object, and we're getting that from our using statement, Microsoft.extensions.caching.memory. So that allows us to use iMemory cache. We're going to set a variable underscore cache using that type. And then in our public cache service method, we're also going to use that iMemory cache again, so we can pass in the variable cache into that and set the underscore cache equal to whatever that cache value is. Then we have a get or create method that we're going to use to either get items from the cache or set items to the cache. In this method, we're going to set our expiration for our cache. We're setting it to new memory cache options, absolute expiration relative to now, and then we're going to set it to whatever the value of expiration is that we pass in. We're using that set method to set the expiration. Now notice that the memory cache entry option is a part of the caching.memory library, and then we're setting the cache to whatever expiration we pass in relative to the current time. So that will give us the opportunity to modify the expiration if the cache is already not set up, and that's how we do that in that method. Those are the areas of code that you need to fill out for this lab. Instant communication powers our most dynamic apps, from video calls to multiplayer games. At the heart of these interactions, there's real-time communication, the technology transforming how we connect, work, and play. In this video, we will define real-time communication and its relevance in modern applications. Let's begin by defining what real-time communication is. It enables information to be sent and received almost instantly with minimal delay, ensuring seamless and interactive experiences. For example, during a video call, you view and hear the other person as they speak, making conversations feel natural and smooth, even when you're far apart. Now that you understand what real-time communication is, let's explore some of its key concepts, starting with WebSockets. WebSockets are a crucial communication component of real-time communication. They enable two-way communication between a client and a server over a single persistent connection, allowing data to flow seamlessly in both directions. For instance, a stock trading app uses WebSockets to instantly update prices, keeping users informed in real time without refreshing. WebSockets are powerful but can be hard to manage. For example, scaling to handle thousands of users simultaneously constrains servers. Developers must address challenges for smooth and reliable performance. To simplify real-time communication development, Microsoft introduced SignalR. SignalR simplifies real-time communication by managing fallback mechanisms like server-sent events and efficiently handling large-scale connections. SignalR automatically selects the best available data transport protocol and manages client-server connections, reconnections, and message routing. This ensures that apps operate smoothly across devices and browsers. It also makes it easier to build apps like collaborative editing tools where multiple users can make changes to a document and instantly review the updates. Now that we've explained how WebSockets and SignalR works, let's explore how real-time communication makes applications interactive. Real-time communication powers features like live chat, multiplayer gaming, and collaborative tools. For example, in video conferencing apps, WebSockets enable smooth and efficient audio and video streaming, while SignalR ensures compatibility across a wide range of devices and browsers by seamlessly managing transport mechanisms. In this video, you learned about real-time communications and its relevance in modern applications. Real-time communication is essential in modern interactive applications. As technology evolves, its ability to create seamless, instantaneous interactions will remain a fundamental part of innovation. When you're creating client-server apps, sometimes it's important and necessary to broadcast messages to a bunch of different clients all at the same time. There's a library in the .NET framework called SignalR that allows you to do just that. It not only will broadcast to multiple clients, but it also keep everybody up to date in real time. I'm going to illustrate and demonstrate how SignalR works in this screencast. You can see in my project, I have 3 different projects set up in this solution. I'm at the root of the solution, and I've got a client project, a server project, and a shared project. And I'm going to show you how the server will send messages using SignalR to multiple clients at the same time. The shared service is used by both the client and the server. It's fairly simple. It's just a single class with a model. We have a chat messages.cs file, which creates a chat message object in both our client and our server. And this just sets up the data object that we're going to use both to send messages and then broadcast them out from the server and the client. The shared library is pulled in by both the client and the server, and then is leveraged in the application. Now let's go to the server project. We've implemented SignalR in this project. I'm going to go to programs.cs so you can see where we're using SignalR. I've added the SignalR library here in builders.services.add SignalR, so that allows us to use it throughout the application. I've also got a chat hub mapping here that allows us to use the hub in our server so that we can broadcast those messages when we need to. The final thing I've added is a CORS option. CORS is essentially a permissions library so that when messages are coming from different sources, this allows the clients to trust those sources. And I've got it really loose here for our demo, but you can set CORS so that you can restrict it only to certain servers and to certain sources. But we have to add that so that our clients know that they can trust the server. Now I'm going to go into chathub.cs. This is the core of how we broadcast messages from our server. The chat hub just has a send message method with the message being sent in the parameters for that method. It gives us a timestamp, so we set a timestamp for the message. And then you'll notice this await. This is an async method, so you'll notice the await keyword. And then the clients.all.send async is where we send messages to all clients that are subscribed to the server messaging system using SignalR. The .NET library wraps all that up, so you don't have to do a lot of hand coding. It just broadcasts that message out to any client that's subscribed to the server. Now let's go on to the client side. And in the client side, we've implemented a chat service class. And this chat service class uses SignalR as well. We're using the SignalR.client library, and we're going to use that library to essentially set up a connection to the server once the server is running. We create a variable called _hub connection using the hub connection type. That hub connection is a part of the SignalR library, and it allows us to create a real-time connection to the server. And what's interesting about hub connection is that it is real-time. So as messages are sent from the server, you don't have to pull the server to get new messages. That hub connection will maintain a real-time connection to the server and grab whatever messages are being broadcast. Then we have an action. This is just an event handler so that when a message is received, something happens. And you can see it's using the chat message type in that action. So we know what to do when the chat message comes in. We have a chat service method that we've written. And in this, we have the hub connection, and the connection is going to link to the server, and you'll see that chat hub route there at the end of the URL. And that is the route that we set up in the server, if you'll recall, so that the client knows what URL to connect to for that real-time communication. So this hub connection is establishing that SignalR real-time connection to the server, and it will maintain that connection. Then we have a parameter for with automatic reconnect. In case the connection drops, it'll automatically reconnect, and then the build method that brings it all together. Then we have an event hub connection on. So when a chat message comes in, this event fires and we get the receive message event handler, and the receive message event handler will invoke the on message received event so that we can actually see the messages in our client application. So we have our start async method, and that method is called from our chat page, our chat.razor page, which we'll look at in a moment. And that just starts the connection and gets the connection established to the server. And then, of course, we've got our send message method that we use to actually send the message out. So when we're in our client application and we hit the send button, it'll call that send message method, passing in the message, and then send it through the hub connection to the server. And then it'll broadcast to all the other clients that are attached to the server using SignalR. So let's go into our chat.razor. This is the page that we're using for our actual messaging. You can see we have some input fields, the username and the message that we're going to send, and then a send button, which is the on-click button. And that send button we'll call the send method in our @code directive. And you can see we're using the chat service.send message with the message body being sent in that message. So that send message just checks for some variables to make sure it's not empty. It establishes a new message object with the user message and timestamp, and then it sends that through the send message method in our chat service.cs file. When the page is initialized, it's going to look for new messages, any new messages that have come in. It will add those messages to our message library, and then it will invoke the async state has changed, just letting us know that something has happened. There's a new message that's arrived. And then finally, in our onInitialized async, we actually do start that connection when the page loads. So we don't do anything until the page loads. When the page loads, we go out to chat service and we start that connection to the server. You remember in start async, it creates a connection to the hub that is running on the server at this URL that we've established in the hub connection. So we do that in our chat.razor page. We start that when the page loads. So we're ready to go. We've got everything set up. We can now run the server and then run our messaging through the client. So the first thing I'm going to do is go to the server. You can see I have two PowerShell terminal windows set up, one for the server, one for the client. I'm on the server one right now, and I'm just going to run the application. So now the server is running. You can see it's running at localhost with the port number of 5137, which is the same port number that we set in our chat services. And it's going to route to the chat hub location, and that's where it's going to listen for messages. So not that the server is running, we can let that be. It's going to run in the background. And now we'll run the client. Okay, so the client's running and it's on host 5132. So I'm going to go ahead and browse that. And then I'm going to go to my route. There's our message application. So now we can send messages. Now I'm going to do one other thing to illustrate how SignalR works. I'm going to open up another tab, assuming this is another client. So this could be on any computer. This could be on a different person's computer. It could be on my mobile device. I'm using two tabs to illustrate two separate processes, two separate clients that will get broadcast to. And I can do the same. I can add a third if I want. In fact, let's do that so we can see how this works. And I'll go ahead and add a third one. Now in my first tab, I'm going to send a message. My username is user. Send a message called hello there. Now, when I send the message, we should see that message show up not only in this window, but in the other two client windows, because we're using SignalR to broadcast every client that's attached to the server. I get the user says hello there. It's sent it at this time. And then when I go to these tabs, it doesn't look like anything's changed, but I'm actually changing tabs. The message has been broadcast to every single client using SignalR. I'll send another message from user 3 because we're in the third tab. And I'll say, well, hi. And then I'll send that message. User 3 said, well, hi. That shows up in user 2's tab as well as user 1's tab. So using SignalR, we're able to broadcast messages. We set up our server. The server is listening for messages. The clients then send messages to the server using SignalR, and then SignalR broadcasts to any client that's subscribed using this hub connection to that server. That's a great way in Blazor to have real-time updates and allow your client applications to get information in real time.
In this lab, you're going to learn to implement real-time communication in a Blazor server application using SignalR for sending and receiving messages. In step 1, you're setting up the SignalR application. We're going to use the Blazor template to set this up, and you're just going to call the application real-time app, and then you're going to switch to the folder real-time app. And then you're going to add the package Microsoft.asp.NET core.signalr, and you're going to do that in the terminal. And that will allow us to use SignalR so that the client and the server can communicate in real time. Next, you're going to configure the SignalR hub. And for that, I've got a hubs folder and then a chathub.cs file. And we're just going to simply add the send async method to this. We're going to call the clients.all.sendAsync method, and that's in turn going to call the receive method on the client side. So there's a layering of method calls in this chat hub, and that's so we can send messages to a specific client. And you'll notice that we're sending it to actually all clients here. So we have the clients.all.sendAsync. So any clients that are connected to the hub will be sent the message to the client's receive message method. We're going to send two different pieces of data in that send async method. We're going to send the username and then the message that's passed into the send message method. We'll send those along to the receive message on the client side. In step 3, we're going to add SignalR to the application pipeline. And for that, we'll go to program.cs. We're adding SignalR at the top, so we're going to use the SignalR services. And then we're just going to map the hub here. So we're going to map it to our chat hub, which we created earlier. And we're going to use the route chat hub so that clients know how to get to the specific service when they connect to the server. The client can connect at that route. And then in step 4, we're going to set up our client side. So in this application, we have the client just in a single application. In the real world, we would have this as a separate app, but for demonstration purpose, for this purpose of this lab, we all have it in the same application. So in the onInitialized async method for this page, you're going to set the navigation for the hub to /chathub, which we just set in program.cs. so that clients know how to get to the hub. And that's our URL, that's our route that we're going to use. And then hub connection on is what happens when a client connects to the SignalR hub. And notice we're using receive message again, which is the method that the hub will communicate with when it's sending messages to the client applications. And there we're passing in again the user, which is the username, and then the message, which is the message body. And then to the messages list, which we've created up top, we're going to add the user and the message to that list.
So that gives us the ability to create a list of messages that are coming in from various clients, and then they're going to be sent out to other clients based on who's connected to the hub. And then in the hub connection closed, if the hub connection does end up getting closed, we're going to wait for 5 seconds. We're going to use that task.delay 5,000. 5,000 is 5 seconds. And then we're going to reestablish the connection again. So if the connection's closed, we're going to use hub connection and then start this to synchronize with the clients again. Then that's a fail-safe just in case something goes wrong. And those are the steps for this lab. Effective state management is essential in any well-designed application. By mastering state management principles like consistency, persistence, and security, developers can create reliable user experiences while ensuring their applications remain scalable and efficient. In this video, we'll identify core principles and considerations for managing state effectively in full-stack applications. Let's begin by exploring the principles of state management, starting with consistency, a key principle that builds reliability. In the context of state management, consistency ensures that your application behaves predictably and reliably across all its components, creating a seamless and trustworthy user experience. For instance, when a user updates their profile on a social media platform, they expect to have the same change reflected on their mobile app and desktop immediately. Without consistency, the user experience can feel disconnected. Next, let's explore persistence, the principle that enables applications to retain critical data across sessions, providing an enhanced user experience. In the context of state management, persistence ensures that data is retained by utilizing tools like session storage, server-side sessions, or databases. This enables applications to maintain data continuity across sessions and enhance the user experience. For example, imagine adding items to your cart on an online store and closing your browser. When you return later, you expect those items to still be there. By having the items persist in their cart, you keep a user engaged without frustration. Next, let's explore how the principle of separation of concerns can improve your application's maintainability. In the context of state management, separation of concerns refers to dividing an application into distinct areas based on their specific responsibilities, such as state management, user interface, and business logic. This principle promotes organized modular code, making it easier to understand, maintain, and scale as your application evolves. For example, in a to-do list app, the state management layer is responsible for storing and updating task data, including adding, editing, or deleting tasks. Meanwhile, the user interface or UI layer focuses on rendering the task list visually and handling user interactions like selecting a button to mark a task as complete. This separation ensures that changes to the task data, like updating the storage structure or logic, doesn't affect how the tasks are displayed in the UI. Similarly, UI changes like redesigning the task list don't interfere with the underlying logic for managing tasks. This clear division makes the code more modular, maintainable, and easier to debug. The next state management principle we need to explore is performance optimization. In the context of state management, performance optimization involves applying techniques to enhance an application's speed and responsiveness. This is achieved by minimizing unnecessary processing, eliminating redundant tasks, and efficiently utilizing resources to deliver a smooth and efficient user experience. Consider a news app where the same top headlines load every time you open it. By caching those headlines locally, the app can display them instantly without repeatedly fetching data from the server. This saves time, reduces server load, and improves user satisfaction. Now let's explore a final principle of state management, security. Security considerations involve safeguarding sensitive information in your application by employing measures like secure storage, encryption, and access controls. These practices help prevent unauthorized access and data breaches and ensure the integrity of your application. Consider a payment processing app that stores credit card information. If data isn't encrypted, it could be easily stolen. Encrypting this information ensures that even if someone gains unauthorized access, the data remains unreadable, maintaining trust and compliance with data protection standards. In this video, you learned about the core principles and considerations for managing state effectively in full-stack applications. By understanding the principles of state management, you can keep your application operating smoothly and deliver a robust, responsive, and secure experience for every user. When you're working with client-server applications, in many cases, it's really important to make sure that the client and the server stay synchronized. There's many real-time scenarios like a chat app, which we're going to demonstrate today in the screencast, where it's really important that all clients get messages at the same time. You can imagine email applications would be something similar to that. And there's lots of scenarios where you want to make sure that synchronization happens consistently and reliably. So in this screencast, I'm going to demonstrate strategies for managing state across the client and server so that we can make sure that the application is consistent in that way that we want. I have a .NET solution here with 3 different projects loaded. I've got a client side, a server side, and then a shared project that both the client and the server are able to use. This is a solution that I created for a previous screencast, so this may look somewhat familiar. And the server side, this is going to be the listener. This is what listens for messages. This is a little application that you can use to chat and send messages back and forth to different clients. And so the server is going to be listening for those messages. It's using SignalR to do this. So SignalR is a real-time library that developers can use to make sure that all clients that subscribe to a service are getting updates in real time. So it's going to use SignalR to manage those messages. And then on the client side, this is the interface, mainly the interface that we're going to use along with a service that I've created to be able to send and receive messages, send messages to users and then receive those messages. It's a very simple application, but I hope it illustrates the point. The shared library just has a class file for now, where the class is just setting up what those messages should contain. So we've got the user, the message, and then a timestamp. And those are what's sent back and forth between the client and the server. We're going to modify this application a little bit to make it a little more robust than it is as a best practice to show how we can improve how the synchronization and the integration is managed. Before we do that, I'm going to just illustrate how this works. So I've got the client and the server running. I've got 2 terminals windows running here, and I've started up both of the applications. Now I'm going to go to 2 different browser windows. So I've got Chrome on this side, and then on this side I've got Edge. So they're 2 different clients and the same chat interface. This is our Razor file that it was in the client side and the code that I showed. This is the client application, and I've got it loaded into 2 different browser windows and 2 different browsers entirely to show you how this works. You can imagine that these clients could be anywhere in the world, frankly. It would work exactly the same way. So when I send a message from user 1, it's going to show up in the Edge window, which is what I'm in right now. Because we're using SignalR, it's going to send that message to the server application that I showed, and it's going to broadcast that message to any client that's currently logged in and subscribed to that service in the client application. We'll see the message show up here in the Edge window, and we should also see it in the Chrome window as well. So when I click the message, you can see that it synchronizes. It sent the message from user 1. It showed up in the user 1 window and also showed up in the user 2 window. Now from user 2, I'm going to say a different message, and it will show up in the user 2 window, obviously, but then also show up in the user 1 window. So using SignalR and using this application, we're able to broadcast those messages to anybody that's logged into localhost 5132/chat, and those individuals will get those messages. Now let's go back to our application. I'm going to stop both of the services. So I'll stop the client and stop the server from running. And now we can modify our application a little bit. One way we can improve this application is to add a version property to the messages that are sent. A version would just help us know that the messages that are being sent are of a specific type and have come from a specific client. And it just gives us an extra check that we can apply so that when we're sending messages, we don't send duplicates or we're not getting out of sync. To our sendMessage method, I'm going to add a version property. I'm going to first add the property as an int, which is just obviously a number. I'm going to put that at the top of my class file. So I'm going to call this getExistingVersion method, which will get the existing version of a message from the user class. And I'm going to put that in the existing version variable. Now I'm going to create my getExistingVersion method. I'm not going to fully implement it. I'm just going to use this to show how it works. I'm going to add that method to the bottom of my class file. And right now I'm just returning 1. In a real world scenario, if a user tries to send a message multiple times, the clients might receive that message multiple times. We don't want that to happen. So what we would do here is get the existing version of the message before it's sent, and then send only the one that is the latest, the current one. So here I'm just going to return 1 because it'll always be the first message. Now I want to add some logic. So I'm going to essentially say if the message is the existing version, if the current version is the existing version, then I want to essentially return. I don't want it to send an improper message. So I'm going to add that to my sendMessage method. So it's going to check, is the message version less than or equal to the existing version? If it is, there's a conflict. And so we're going to return from that method because we don't want to send the message. And I just have the return commented out for illustration purposes. And then we're going to add a timestamp, and then we're going to send that message to all clients. And what this has done is just giving us an extra check. SignalR is very good at managing the messages and making sure there isn't any conflicts. But this gives us a little bit more control over that so that when we're sending our messages, we're making sure that they're the right messages that we actually want to send. We've added this new version property to our hub. And now I want to make a change to the client side. The client is obviously what connects to the server, and that connection is really important for the clients to receive all the data. Now, SignalR is very good at keeping clients connected. If a connection goes down, SignalR is really good at making sure that the things stay intact. But I want to add some logic to this to make sure that if client closes for whatever reason, if that event is detected, I want to give it a little bit of a delay and try to reconnect. I'm going to have the client manage that reconnection. I've got this chat service method that I've implemented that actually builds the connection. It's calling the chat hub endpoint on our server at 5137. It creates that connection, but I'm going to add another property, an event essentially, to this variable that creates that connection. If it detects that the connection is closed, there's an error that will pass to the event. But then I'm going to do a couple of things. I'm going to have it wait for about 5 seconds, and then I'm going to have it try to reconnect. So I'm going to add this code to our property here. And what that's going to do is detect for a closed event, hubConnection.closed, and then it's going to write to the console in the browser that the connection's been lost and that it's reconnecting. It'll wait for about 5 seconds, and then it'll retry that connection. It'll start async as the method that we use to attempt that connection to the server. You can see that's down here where it creates that connection to the hub. By adding this code, we just make the app a little bit more robust. This is a good best practice. It gives you a little bit more control. You can imagine in a real world scenario where if the connection does go down, even though SignalR may be able to reestablish that connection, by actually trapping the event, you can provide messages to the user, a little pop-up that might say connection is lost, we're attempting to reconnect, so you can give the user a little bit more information. So this is just a good practice to be able to apply to your client and server environment to make that application a little bit more robust. So these are the ways that you can use SignalR in a client-server environment to handle robust client-server interactions, make sure state is synchronized, and some mechanisms you can use to make that environment more usable and more user-friendly. We can also handle these states a lot more gracefully by adding this code to our application. The application did run without it, but by adding it, we can improve the application and the experience for our users.
Efficient state management and seamless client-server communication are the backbone of responsible, scalable, and user-friendly applications. By completing this module, you've gained essential skills to design robust, full-stack systems that can handle the complexities of modern development. We began by exploring the fundamentals of state management. exploring the roles as the foundation of dynamic and interactive applications. Understanding the concept of state has prepared you to build applications that respond effectively to user actions. Next, you learned about client-side state management. Techniques like local state handling, global state management libraries, and caching were introduced to ensure your applications deliver swift and seamless user experiences. Then, we shifted to server-side state management, examining methods like sessions, database management, and server-side caching. These strategies enable you to create applications that are consistent, reliable, and capable of scaling to handle distributed systems. After that, you explored real-time communication techniques, including WebSockets and server-sent events. These tools empower you to implement real-time features like live updates and collaborative tools, enhancing user engagement. Lastly, we reviewed best practices for state management, helping you make informed decisions about tools and strategies while avoiding common pitfalls. These insights ensure your applications remain maintainable, scalable, and efficient. Congratulations on completing the state management and client-server communication module. You've taken an important step towards mastering full-stack integration and building applications that are both robust and responsive. The concepts you've learned here will be invaluable as you continue your journey in full-stack development. Well done. Welcome to Using Copilot for Integrating Front-End and Back-End Code, part of the Full Stack Integration course. In this module, you'll harness the power of Microsoft Copilot to streamline and enhance the integration of front-end and back-end components in your full-stack projects. By mastering these techniques, you'll become adept at writing, debugging, and optimizing integration code while efficiently managing data structures. By the end, you'll be ready to implement robust, high-performance integration strategies for modern web applications. We will begin by exploring how Microsoft Copilot can assist you in writing seamless integration code that connects front-end and back-end components. Integration code is the backbone of communication between the user interface and the server. Using Copilot, you'll learn to generate boilerplate code, implement API calls, and ensure data flows efficiently between the two layers. This skill is essential for creating dynamic, responsive web applications that function smoothly. In debugging integration code, you will focus on utilizing Microsoft Copilot to identify and resolve integration issues effectively. You'll learn how to leverage Copilot's suggestions to pinpoint errors, fix bugs, and refine your integration code. By the end of this lesson, you'll be able to tackle common debugging scenarios with confidence. Next, you'll discover how Microsoft Copilot simplifies the creation and management of JSON structures. From designing schema to parsing responses, you'll gain practical insights into handling data effectively. Mastery of JSON structures ensures efficient data storage and seamless communication across your applications. Then you'll learn to identify bottlenecks, implement best practices, and write optimized code that improves user experience. These skills are invaluable for building scalable, high-performance systems. Finally, in the capstone lesson, you'll bring everything together to implement a comprehensive full-stack integration project using Microsoft Copilot. This hands-on experience will allow you to apply the skills and techniques learned throughout the module. By completing this project, you'll demonstrate your ability to design, debug, and optimize a fully integrated application, showcasing your full-stack development expertise. Using Microsoft Copilot for integrating front-end and back-end code empowers you to streamline development processes and build high-quality applications efficiently. By the end of this module, you'll have the knowledge and skills to write, debug, and optimize integration code, manage data structures, and deliver seamless full-stack projects. Let's dive into the exciting world of full-stack integration with Microsoft Copilot. Building a seamless connection between your front end and back end can feel like solving a complex puzzle. With Copilot,
tedious coding tasks become manageable, empowering you to focus on delivering reliable, efficient integration. In this video, we'll describe how Copilot can assist in generating and refining integration code between front-end and back-end systems. To understand how Copilot assists in development, let's first define what we mean by integration code. Integration code is code written to connect two or more separate systems, applications, or software components, allowing them to work together. For example, it allows the backend to handle tasks like storing data, processing user accounts, or managing product information based on user interactions in the front end. Now that we understand integration code, let's examine Copilot's role in generating it and simplifying application building. Copilot simplifies integration tasks by predicting what you need and suggesting complete code snippets for API calls, authentication, and error handling. It also enhances integration by offering smart suggestions for managing front-end and back-end communication. For example, when you're retrieving data through an API, Copilot can propose streamlined workflows to ensure the data is efficiently accessed, properly formatted, and well organized. Along with assisting with tasks, Copilot promotes best practices for creating modular integration workflows. Modular workflows break integration processes into smaller, reusable steps. For example, imagine you're building a feature to fetch product details for an e-commerce app. Instead of creating a single, large process to handle everything, you can break it into smaller steps, such as one workflow for retrieving product data and another for formatting the details for display. This makes your workflow easier to understand, update, and scale as your product grows. Copilot also encourages an organized approach to grouping related tasks for streamlining project management. For example, tasks related to user login, logout, and registration can be categorized under user management. And tasks for fetching product information or managing inventory can be categorized under product data. This logical grouping simplifies finding and modifying specific workflows, ensuring that changes in one area don't inadvertently affect other areas. Last, Copilot assists with clear naming practices. It does this by analyzing the context of your code and generating names that align with common naming conventions and best practices. For example, when managing user information, Copilot might suggest terms like retrieve user details or update user profile instead of vague names like get data or process info. Clear and descriptive naming ensures that everyone working on the project can immediately understand what each workflow or component is responsible for. This reduces confusion and errors. Copilot helps bridge the gap between front-end and back-end development by automating repetitive tasks and guiding you towards organized, scalable workflows. It's not just a tool, it's a step towards smarter, faster integration. Getting started with writing an application that can integrate with an API can be a little daunting, but with Microsoft Copilot, we can make that job a little easier. In this screencast, I'm going to create a basic Blazor application and then use Copilot to help me get some initial code written so that I can integrate with an external API. So the first thing I'm going to do is create a simple WASM application. I'm going to use the .NET new Blazor WASM template, and I'm going to call my application Copilot Integration Demo. So this will give me my basic app, and then I'm going to open this up in a single instance of. All right, so now we have our application, and it's ready to go. I'm going to open up a terminal window, so now we can interact with our application a little bit easier. So the first thing I'm going to do is prompt Copilot with a request to create the API service that we want to use. So in this app, what I'd like to do is have a service file that I can pass a URL to that is a URL to an external API. And then that service class should return the data that it is called from the API. So it's going to be a very simple app. The service class will make the request. The front end, the user interface, will simply just pass the URL to the service class, and then it will return the data that we want. So I'm going to open up Copilot, and I'm going to paste in a prompt which I've pre-written. So I'm telling it I've created a Blazor app. I want to integrate a web API call. I want to create this new class called API service. It'll accept a URL and then return the response back to the code that called it. I'm specifying that it should be written in C# using basic .NET libraries, and I really don't want to install any additional libraries if I don't have to, so I'm letting it know that it should be very basic. And I ask it to create the class with a method that I can use in my app. In my prompt, I'm giving it very specific instructions about what I want. I've had to do a lot of the thinking ahead of time to realize what I want to create first, and then I can prompt Copilot with the specifics. But what I don't have to do is actually write the code. Hopefully Copilot will give me a response that I can use in my application. So here's what it's returned. It gives me a C# class that I can use to make that call. It's done what I've asked it to do. It's got a get API response async. I pass in a URL. It then uses HttpClient to request data from the external API. It has a response, and then it returns that response to the calling function. So I'm going to copy this out and then go back to my application. I'm going to call this file API service.cs. So now I've got my class file that I can use, and I'm going to paste in that code that Copilot gave me. And now I have the class ready to go, and I can start to work on the next part of my application. Now I do know that I have to integrate this into the program itself. So I'm going to create a singleton instance, and I'm going to have to add that to my program.cs file. So I'm going to go into program.cs, and I'm going to add a singleton. I've got some little helper text there, so it assisted me. I created builder.services, add scoped, and then the API service. So this will allow me to use the API service throughout my application. Now, every time I add new code, I like to just see if it will build, if I get any issues. So I'm going to do .NET build, and let's see if I get any complications or issues. Going through the build process, and it tells me that the build succeeded. So there's no bugs so far, at least compile bugs, but we'll see if it actually ends up working when we get into the code. So now I've got my API service class. The next thing I want to do is create a Razor page that I can use and interact with for my application. So now I'm going to go back to Copilot, and Copilot already has the context of what I want to do. I've told it the kind of app that I want to write. And so it's provided this class. So with that context, I'm going to give it another prompt. And in this prompt, I'm telling it that I want to create a very simple Razor file that I can use to make calls. And I want to be able to pass this very specific API call. This is a test API that I can use to, test my code. And it's just going to return some dummy data back to my application. So I'm giving it the specific URL I want to call, and I'm telling it that I want to display whatever the results are from that API call to the screen. I give it the name of the file that I'd like and the route that I want to use when I open up the application. So I'm going to go ahead and prompt Copilot with that specific ask, and it's giving me some code back. So you can see it's calling the API service get API response async. It knows what that method is because it created the method for me. It's going to pass in that specific URL that I asked it for. And then up here, we can see our HTML, where it's going to process the response data and hopefully present that on screen when we get it back. It's also telling me in the response that I need to create the Razor file called fetchdata.razor in order to make this call. And it's given me the route here, the app page/fetch. So it seems like it's done everything I've asked it to do. So I'm going to go ahead and copy that code out using the copy feature. I'll go back into my application, and then in the pages folder, I'm going to create a new page called fetchdata.razor. And now I've got my page, and I'm going to just paste that code in. So now I've hopefully got everything that I need. I am seeing an error here. It's saying the name can't be the same as their enclosing type. So what that means is I've got the file name called fetchdata.razor, and then I have this name called fetchdata. So what I'm going to do is just change the name of my file, fetchdata page. And that should solve it. Copilot obviously didn't have enough awareness there to not name the task the same name as the page, but we were able to quickly fix that bug. If I wanted to, I can go back into Copilot, explain the error that I was getting, and it would help me fix that problem. So let's go ahead and build this again to make sure that everything compiles fine. All right, so we've got one warning, which we can ignore for now. These are just things that we can fix over time. But for right now, we have a build that our application that's compiling. All right, now we can go ahead and test it. I'm going to do that by typing .NET run. All right, now my app is running on localhost 5170, and I can get to that by control clicking, and it should open my browser. Okay, and there's our app. This is the WASM template basic structure. So we have to browse to fetch. That was the route that we told Copilot that we wanted to go to. So I'm going to go to fetch. And if everything works properly, I should be able to click this fetch data button. And there it is. It gives me the code from the API call. So when I click that fetch data button, the application sent this URL, which is an external URL, to our appservices.cs file and called get API response async. It passed in that URL. It then went out to the internet using this HttpClient get async and waited for the response from that API, put the response in response body, and then return that to the fetch data page Razor. And when that response data value was filled, because it returned from the API, then it showed up in the response data element that was in our HTML section of our application. So this is just a very simple way that you can use Copilot and Copilot code that it provides to get started with an integration app. Sometimes that blank code is very hard to get started with, but Copilot can get you over that initial code writing. And now I can continue to modify this and use Copilot to make this application even more interesting. Smooth integration between the front end and back end is the foundation of any successful application. However, this process often comes with challenges that can disrupt functionality, data accuracy, and user experiences. In this video, we'll describe common issues in front end and back end integration and how Copilot resolves them. To understand these challenges, let's explore some integration issues that can arise when systems try to communicate. We'll start with the common issue of connection failure. A connection failure occurs when the front end cannot establish communication with the back end, leading to failed data requests. This issue disrupts the flow of information and prevents the application from functioning as expected. When a website tries to call a server but gets no answer, the front end and the back end aren't connecting. To fix connection failures, developers often check things like making sure the server is running or checking that the API endpoints are correct. Once the connection is restored, the next challenge is ensuring that the data exchanged between the front end and the back end adheres to the correct format, like JSON structures, for seamless processing and functionality. JSON structures provide a standardized format for storing and exchanging data between the front end and the back end. They help ensure consistent and reliable communication. For example, if an app expects a number for age, but receives text instead, it might give an error message or even crash. Aligning data formats ensures that the app processes information correctly and receives the correct input. After ensuring the data is correct, the next step is ensuring it can be securely shared between systems, which is where CORS or cross-origin resource sharing errors can arise. CORS is a browser security feature designed to regulate and enable safe communication between different domains, preventing unauthorized access to resources. For example, if a recipe application needs to retrieve data from an API hosted on a different server, the API must grant permissions by setting the correct CORS headers. Without this setup, the browser will block the request to protect the user's security. It's also important to focus on how performance bottlenecks can affect an application's functionality. Slow database queries, overloaded servers, inefficient code, and limited bandwidth, as well as too many simultaneous user requests, are common causes of these bottlenecks. These can slow down an app, such as a shopping site that takes too long to load large product images. Compressing data or optimizing transfers are methods that can be used to speed up the app for users. Let's explore how these three common issues can be resolved in an example using Copilot. In a project, integration challenges were addressed systematically. Copilot identified and corrected a server URL to fix connection failures. Copilot also identified mismatched data formats to ensure compatibility by utilizing JSON structures. Then it helped configure CORS headers to secure cross-domain requests. And finally, Copilot recommended compression techniques to enhance performance. This approach demonstrates how potential roadblocks can be managed efficiently to create a seamless application experience. In this video, you learned about common issues in front-end and back-end integration and how Copilot helps resolve them. Integration issues can hinder the creation of efficient and seamless applications. With tools like Copilot, developers can overcome these challenges and focus on delivering exceptional user experiences. When you're attempting to integrate back-end and front-end code, sometimes it can be difficult to find and fix bugs, particularly because you're working with two separate systems. The screencast is going to cover how to solve problems with that integration using Microsoft Copilot. Copilot can help save time, detect errors, and then fix them. So I've got a very simple console application here that makes a call out to an external API that returns fake data, JSON placeholder.typico.com. We can use this URL to test API calls and get data back. This application has some general bugs, and we'll attempt to use Copilot to fix those bugs. And then it has integration bugs that I'll work with Copilot on trying to fix those integration bugs as well. So looking over the code, there's some red lines under some of the areas of code. There's clearly a problem here. Some things aren't working properly, and we can test that by trying to build the project and see if it will build properly. So I'm going to do that. I'm going to build this and see if we get some error back. Yeah, so it failed with 2 errors, so we're not going to be able to run this. So I'm going to use Copilot to help me figure out what's going on with this code. And again, these are just general bug fixes, but I'm going to use Copilot to help me sort out what's happening here. So I'm going to grab all the code from my project. This is a simple app, so I can copy and paste all the code. I can get as granular as I'd like with Copilot and just paste in certain functions or even certain variables. But I'm going to paste in the whole application because it's so small. So I'm just giving a very simple prompt, describing what the problem is, the code won't build. And then I'm going to ask it just to go through the code and see if it can figure out what errors there are and help me fix those errors. So I've pasted in the entire code from program.cs, and now I'm going to ask it to see if it can solve that problem for me. So it lets me know that it sees a few issues. The main method should have a task return type. Wait keyword is missing from the method, the getString aString method, and deserializing the response into list user, but the class is named data. So it's going to attempt to fix those items for me. You can see in the code that it provides, it added the task. It also added the await keyword here. It still keeps data here, but it's using data as the type when it returns the information. So I'm going to copy this code out. Many times what I'll do with Copilot is I'll just look at specific lines of code and make the modifications in my own application. But here I'm just going to paste in the code that Copilot gave me with those changes. So I've got my task, I've got my await, and I'm using data as the type. This should hopefully solve the problems with the build. Let's go ahead and try to build it. So the build is compiling now, and now we can attempt to run it and see if we can get our data back. So this application is a simple web API call. It's using this JSON placeholder.typico.com as the endpoint. And that's the server side. And then the client side, obviously, is this little console app. And it's going to attempt to grab the user data from that API. It uses this client.getString async call to grab a response, which is the data set of users. And then we deserialize those users into our user object, which is called data now. And then we will populate the individual properties using that deserialized method. So let's go ahead and try to run this. We should see a list of user data returned when we call this. Okay, there's definitely a problem here because it is getting some data, but it's not getting the entire data set. We can see there's a comma there. So it's supposed to return username and user email, but it's not getting username for some reason. We only ask Copilot to help us understand what's going on. What I'm going to do is grab the URL for the API call. And now that Copilot has the context for my app, it knows what my data types look like. I'm going to let it know that I'm getting improper response and to help me fix it. All right, so what I've done is I've essentially given it the endpoint so it can analyze the data types. And I'm letting it know I don't want to add any new fields. I just want to make sure the fields that I'm using are correct because it just seems like something's not aligning between the front end and the back end. So I'm going to ask Copilot to help me figure that out. All right, it says, here's the correct structure based on API documentation. So it actually analyzed the API documentation, and it knows that the full name field has to be renamed to name. It also adds a geo class, which we can choose to accept or not accept. For now, I'm just going to change the full name to name and see if that fixes my problem. If it doesn't, I can come back to Copilot and grab some of that other information that it gave me. So I'm going to change this property to just to name. And it's going to populate my name string, and let's see if that fixed the issue. So we'll rerun the application, and there we have it. So now it's got the name as well as the email address. So the error that I had made was that I was using the improper JSON property, which is the property that is returned in the response. On the API side, it's actually called name. Copilot was able to figure that out. It went out to the URL, analyzed the return type property names, and made sure that the names in my class and my JSON property names were actually the right ones. So now the application is working properly. I want to ask you one more question about this origin line, the default request headers. I just want to make sure that's correct and to see if there's anything I can do differently there. I have an intuition that something's not quite right there, but I want to ask if I can fix it. So it says the header is mainly relevant when making requests from a web page to a different domain. Since you're making the request from a console application, the header is not necessary. And then it tells me how I can actually use it if I do need it. So let's go ahead and comment that out and see if we actually need it, if it runs without it. I'm going to comment out the origin. In some contexts, that may be valuable, and here it does not appear to be. Let's go ahead and run that. And it returned the records without the origin header, so I actually didn't need that. In some contexts, if you don't have the correct origin header set, the application will not be able to make the call from the API. So Copilot may recommend that you add that in and give you the correct way to set that origin header so that you can actually make those calls. So using Copilot, you can fix some integration issues between the front end and the back end. Copilot makes it easier to find issues and debug them. And it will actually provide you with corrected code many times so that you can get your issues solved more easily.
Whenever you shop online or check the weather on your phone, JSON works behind the scenes to transmit the data you experience. Understanding how JSON structures and moves data is essential for building the seamless experiences we rely on daily. In this video, we will identify the components of JSON and explain its use for transmitting structured data between front-end and back-end systems. Let's begin by exploring some key concepts of JSON structures, starting with understanding what JSON is and why it's so widely used. JSON, or JavaScript Object Notation, is a lightweight data format for exchanging information. Its simplicity makes it an ideal choice for web applications. JSON is also compact, requiring less space to communicate the same data compared to other protocols like XML. This helps improve performance. Additionally, JSON is inherently easy to work with in JavaScript, as it was originally designed for seamless integration with JavaScript-based systems. Now that we've introduced what JSON is, let's explore its core components, starting with key value pairs. Key value pairs are the fundamental building blocks of JSON. A key is a label that identifies a piece of data, while the value is the data itself. Together, they form the core structure for organizing information in JSON. For instance, in a user profile, you might have a key called name with a value like Alice. This helps the system quickly retrieve Alice's name whenever it's needed. Next, we'll examine arrays, which allow JSON to handle multiple pieces of related data. Arrays are a structured way to group multiple pieces of related data into a single list in JSON. They provide an organized format for handling collections of items efficiently. Arrays in JSON group related items into a list. For example, imagine using a JSON array called days of week for a scheduling app. This array can consist of days of the week like Monday, Tuesday, Wednesday. This structure allows the system to manage all the days collectively, enabling efficient operations like sorting or filtering. Sometimes items need more details, which is where nested objects come in. Nested objects are JSON objects placed within other objects to logically organize related data. Think of them as folders within folders. Each level groups related information together.
This structure simplifies the handling of complex data, making it easier for systems to process and manage. In JSON, this can be represented using a nested object, where an address key holds another object as its value. For example, an entry for Alice could include an address object as a key, with subkeys like city, which is New York, as the data, and zip, which is 10001 as the data. This structure makes JSON a powerful tool for organizing and transmitting detailed product information efficiently, ensuring seamless communication between the app's front-end and back-end systems. In this video, you explore the components of JSON and its critical role in transmitting structured data between front-end and back-end systems. By understanding its structure and use, you've gained insight into how JSON enables seamless communication in modern applications. So when you need to create complex JSON structures, it can be a little bit challenging to get started. So I'm going to use Microsoft Copilot to help me create a basic JSON structure and then use that in a console app in C#. So I'm going to create that console app first, and then we can use Copilot to help us figure out what our JSON should look like. All right, and just call it JSON structure app, and then I'll open that up in a separate instance. All right, so now we have our application, and now I'm going to go to Copilot and ask it for some help creating this structure. So I'll give it a prompt describing what I have: a new console application in Visual Studio Code. I want to create a JSON structure for vinyl record album collection, and then I'm asking it to create that structure in C# for me. So it's got the JSON structure. There's arrays. This is a complex structure where it's got the tracks, the different albums, and other data there that we can actually use in our JSON structure in our application. So I'm going to take the code that it's giving me. The code, it will allow me to actually use that JSON in my code. So I'm going to copy that code out and paste it into my application in program.cs. I'll remove everything that's already there because that's templated code, and then I'll paste in the code that Copilot gave me. The first thing I want to do is just make sure that this code compiles. I can see that it might be some errors in here already, so I'm going to see if the code compiles. I'm going to open up a terminal window and see if this will build for me. So it gave me one error. It says vinyl collection member names cannot be the same as their enclosing type. The problem is that the class is called vinyl collection, and then it's got a member called vinyl collection as well. I'm going to have to change that to something else. I just call it albums. Now we'll see if that will actually compile. Now it's giving me more errors because I changed the name in the class, but I didn't change it in the rest of the code. So I'm going to go ahead and do that. Now I could have used Copilot to actually help me with this. I could have told Copilot what the error was, and Copilot would have helped me debug that. But it was just a simple fix, so I went ahead and did that myself. Now we'll have to tell Copilot that we did change the name. So I'm going to select that and copy it to the clipboard. And the next time we use Copilot, I will ask it to update that name in case it gives me some new code. I'm going to ask it to add a new feature. I added that last phrase, so in case it gives me new code, it will update the property name appropriately. Let's see what it provides here for this complex structure. So now it's given me a new album structure where it can add multiple albums in an array. And you can see that here. We've got an array of albums now, and you can add more arrays of albums if you want. So this will just allow us to organize these a little bit more easily if we want to in the future. So it's giving me a new structure as well as new code. And you can see here that it did update the Vinyl Collections album appropriately. So I'm going to copy that code out and paste that into my program. I'm going to select all the code and paste that in. And we'll go ahead and build that again just to make sure that it builds properly. And it does, and so we're in good shape so far. Now we've got a complex JSON structure, and Copilot helped us build this. It's got some sample data in here. We can continue to add other sample data if we want to. Then it will write out the deserialized albums as we need them. Now, this is a very simple application. We can create a better user interface. But let's run this. So it just told us that it deserialized one array of albums, and we can add more albums to that if we want. I'm going to do one more thing. I want to take the album collection out of the code itself and put it in a separate file. And I'm going to ask Copilot to help me do that. So we're going to move the data to a separate JSON file and then read it into the program. So this is the JSON file that it's going to give me. I'm going to copy that out. Then it's also giving me the C# code that I need to read in that albums.json. I'm going to go back to the code, add the albums.json first. And then I can paste that into the code. So there we've got our complex JSON that we want to use. And now we'll go back to Copilot and grab the C# code and paste that into the application. And I'm going to select the entire thing and paste that in. Our code's a lot simpler because it's reading in the file and it lets me know if there's an error reading in the file, but it's going to read in the file albums.json that's up here to the programs.cs. And then it's going to read that, deserialize the album list. So I'm going to go ahead and run this again. It should give me the same response, and it does deserialize one array of albums. Now we can test this a little bit by actually writing out the album names. I'm going to ask Copilot to give me code that will do that. So it's going to loop through the deserialized album data and print out the album names to the console. I can just go through this code and try to figure out what is new here. It looks like the Copilot just added a for each loop after the code was deserialized. But just because the code is small and the application is so small, I'm just going to go ahead and paste that entire code block into my application. And let's see how this responds when we run it. So we have two albums in our collection, Thriller and Back in Black. The code was able to give me both of those albums by iterating through. You can expand upon this and make this even more interesting and rich. Now all of our albums, our JSON, is stored in a separate file, and our program will then read that in, and we can do various things with it. So using Copilot, you can create complex JSON structures as well as manage them and use them in a user interface.
Integration code is essential for seamless communication in software, but even minor inefficiencies can cause significant slowdowns. These inefficiencies, often referred to as bottlenecks, are like traffic jams in your code, points where the flow of data or processing slows down, creating delays for the entire system. For example, imagine a busy highway where multiple cars merge into a single lane. This creates congestion that slows everyone down. Similarly, in software, bottlenecks occur when specific tasks or processes take longer than expected, impacting overall performance. In this video, we will explain common bottlenecks in integration code and strategies to address them with Copilot. To begin, let's explore some key bottlenecks you might experience in code, starting with redundant API calls, a frequent culprit behind slowdowns. Redundant API calls are duplicate or unnecessary requests made to an API, often leading to wasted resources and slower performance. Imagine a weather app that continually asks the server for your location data, even when it hasn't changed. Each duplicate request wastes time and resources, slowing down the app and putting unnecessary strain on the server. Caching strategies can help prevent these redundant calls by storing and reusing data when it's still valid. While Copilot might not directly highlight these patterns in your code, its suggestions can help you write cleaner, more efficient code that avoids such problems. Next, we'll address latency issues that cause delays between the front end and back end. Latency issues refer to problems that create unnecessary delays in communication between the front end and back end. For example, this can happen if your server processes requests inefficiently or if database queries are slow, leading to noticeable delays for the user. Consider a sports app displaying live game scores. If the back-end server takes too long to fetch updates, the app might display outdated scores instead of the most recent score updates. Copilot will not explicitly highlight areas in your code that might cause latency issues, but its suggestions can help guide you towards writing more efficient and optimized code, indirectly helping you avoid latency issues. Finally, let's examine serialization overhead, which impacts how data is transferred between systems. Serialization overhead refers to the extra time and resources required to convert data into a format suitable for storage or transmission. For example, using overly complex or inefficient serialization methods can slow down data transfer and add unnecessary delays.
Recall that serialization makes data transferable between systems by converting it into a suitable format. However, repeated or inefficient conversions can add unnecessary processing time, slowing down communication. Using efficient libraries can help minimize serialization costs and improve performance. Here, Copilot may not explicitly suggest libraries to reduce serialization costs, but it can help you optimize your data retrieval or serialization logic. This can make your code more efficient and reduce overhead. In this video, you learned about some of the common bottlenecks in integration code and strategies to address them with Copilot. Improving integration code isn't just about optimization, it's about creating systems that are robust, scalable, and equipped to handle modern demands. When you're writing back-end or front-end code, it's important that your code is as efficient as possible. It's hard to find areas that you can make more efficient, but you can use tools like Microsoft Copilot to help you analyze your code and suggest changes that will improve its efficiency. In this screencast, I'm going to use Copilot to take a very simple app and look for efficiencies, redundancies, and ways that I can optimize it. I have a very simple application here. It's a console application that makes 3 API calls. You can imagine in a real-world scenario where you're getting data from 3 different endpoints, and then you take all that data and you merge it together or you do things with it. Here I've got 3 different endpoints that I'm calling, and I'm getting data from those endpoints. There's probably a way to make this a little bit more efficient. Making those calls one after another can slow the application down and certainly doesn't seem efficient. So I'm going to use Copilot to help me make changes. So the first thing I'm going to do is prompt Copilot to make this code that I have more efficient. So I'm going to take this code and prompt Copilot with it. I set up my prompt, essentially telling it what I want it to do. And then I'll go back and copy my code into Copilot and see what it returns. Now, it doesn't really need to know too much about my application at this point. I'm just going to show it the code because I gave it a very specific instruction that I want to make this more efficient. I don't have to provide it with too much more context. And then it should return with a little bit more of an efficient way to get the code back. So here we have a single tasks array, and it's going to use this task when all to call them. So this is a little bit different of a way to accomplish the same goal. Instead of waiting for each one to return, it's going to call it essentially as a block and provide the results in a variable called results. And then we can iterate through each of the results and print the results to the console if we want. So I'm going to copy that code out, and then I can paste that into my application. I've got my code that Copilot provided, and it is a little bit more efficient. Using that task when all approach, it helps me to improve the way that the API calls are made. Now, the next thing I want to do is implement a caching strategy. Caching ensures the data is fetched from the server only if it's already not on the device or in the cache. So this reduces server load, and it also prevents the application from having to go out to the server and retrieve the data. So I'm going to prompt Copilot again to ask it for helper method for caching. And I'm going to use a simple prompt for that. Now that it has the code as a part of its knowledge, I can just ask it to implement a caching strategy. Because it has that code, now I can just say implement a caching strategy for the API responses. And it should take the code that it already has as its knowledge and then provide an approach where it will cache the responses and then only call it to the server if the cache is expired or not filled. So let's see what Copilot provides back. So it creates a new cache variable at the top here, and then it tests the cache to see if there's a value. If it has a value, it'll return the cache response. Otherwise, it will go out to the endpoints and retrieve the data that it needs. So it works in a very similar way to the way that we had before, except now it's adding that cache feature. It's using the task when all again. So it preserved the original modification that it gave us, and now it gave us this new modification. So I'm going to go ahead and paste that code. Now, many times I may not paste the entire code block from Copilot, but in these cases, because the code is so simple, I'm just going to take the entire block that Copilot provided and just paste that in. So now we have our caching strategy. So it will retrieve the data. If the data is in the cache, it will use the cache data. If it's not in the cache, then it will go out to the endpoints and gather the data. All right, the final thing I want to do is refactor this code a little bit for clarity, just so that it's easier to read and easier to manage. Because it's so simple, there's not much that Copilot's probably going to be able to do here, but we can continue to iterate and improve each time we update our code. And this is important because as you develop code in increments, you want to make sure that those increments are as efficient as possible so you don't have to go back later once you've got a number of methods or a number of lines of code and try to make that more efficient at the end. It's just easier to do it in an iterative way this way. I'm going to give Copilot another prompt, and I'm just going to ask it to refactor the code for clarity. A very simple prompt, but it will try to go through that code and make it simpler and easier to read. So what it's done is it's made the code a little bit more concise, and it's put in some feedback in the console write line so we can see what's going on. It extracted the caching logic it's telling us into a separate method, and it added comments to explain key parts of the code. Now notice it stated that it added comments, but it didn't actually add comments. So we can actually prompt Copilot and let it know that it forgot to add the comments. So I'm just telling it that the comments don't appear to be in the code. Can you please add them? And again, that will help improve readability and the way that we can manage the code later. Now it has gone back in and kept the original changes that it made, but also added those comments. So we can go and copy this code back. It also gave us the entire application. So I'm going to select all and paste this in. And now it has all of the using statements that it needs. It's got the comments that we asked it for, and it's made the code a little bit easier. It's got this get cache data async method that it's using to retrieve the data from the endpoints, and it's still using that when all had seen earlier. So even if you're not quite sure how to optimize your code, you can use a tool like Microsoft Copilot to help you analyze your code base and then provide feedback. You can also learn a lot as you see how Copilot provides those updates, and that can help you as you write future code as well. Building a full stack application is like constructing a house. You need a solid blueprint before you begin. With a clear plan, you can ensure that every part of your application works together seamlessly, avoiding issues later. In this video, we will describe the planning process for full stack integration, including deciding on APIs, database design, and user flows. To start planning, we must first understand the main steps for building a full stack application. First, we need to identify the key components of the application we'd like to build. A full stack application consists of three main components. The first is the front end, the part the user experiences on screen and interacts with. Imagine a shopping website where you can browse items, search for products, and add things to your cart. These actions happen in the front end, which communicates with the back end to process your requests and display the results seamlessly. The backend is where all the behind-the-scenes work happens to keep everything running smoothly. For example, when you add an item to your cart, the backend updates the cart and calculates the total price for you. It handles the data processing and logic, ensuring the information is ready for the front end to display accurately. The final component is the database layer, which acts as the memory of your application and stores all the essential information. It tracks things like available products, what's in your cart, and even your payment history. Together, the front end, back end, and database form the foundation of a well-organized and reliable application. However, to ensure these components work together effectively, we need to define API endpoints. API endpoints are specific URLs used by the front end and back end to exchange information. For example, when you browse products in a shopping app, the app uses an endpoint to request data from the back end, which responds with a list of available items. Similarly, when you add something to your cart, another endpoint processes the request to update your cart. These endpoints act as the links that enable seamless communication, ensuring the application functions as a cohesive system. The next step is selecting the tools and technologies you want to use to build your application. Specific tools are essential for building and connecting your application's components, each serving a specific purpose. For example, to create a shopping website, you can use a framework like Blazor to design a clean and responsive front end. And on the back end, a tool like .NET Core can handle logic and data processing. Remember to also include security and authentication tools to protect users' data when they log in or make purchases. The right tools streamline development and enhance reliability and security, ensuring your application is efficient and trustworthy. Next, you need to consider how to map out user flows. A user flow represents the steps a user takes to complete specific tasks in your application. It helps you structure and understand how users interact with different system parts. For example, on a shopping website, the user flow might begin with browsing products, and then the app retrieves data from the back end to display to the user. Next, the user adds an item to the cart, prompting the database to update with the new cart contents. Finally, the user checks out, and the back end processes the payment. Planning these steps carefully ensures your application is intuitive and that all components work seamlessly together. As a last step, consider AI tools such as Copilot for planning assistance. These tools work as helpful assistants, offering suggestions based on the steps you've already planned. For instance, they can suggest how to organize your API endpoints or offer templates for common workflows. Imagine needing a structure for a user login system. An AI tool like Copilot can help you plan how the front end, back end, and database interact, eliminating the need to start from scratch. These tools are optional, but can save you time and give you new ideas. In this video, you learned about the planning process for full-stack integration. With a clear plan, you can ensure that every part of your application works together cohesively, creating a strong foundation for a reliable and efficient full-stack application. When you're creating a client and server application, you want to make sure that your client and your server are communicating in the right ways, using the right parameters, the right calls, and all the rest. Knowing how to do that and making sure that everything lines up can have its challenges. We can use a tool like Microsoft Copilot to help us get past those challenges and at least get started writing client and server applications that communicate properly. In this screencast, I'm going to use Copilot to do just that. I have a server application, a web API application, and a Blazor client application. I don't have a whole lot of code that does much in here other than the templated code that the .NET framework gave me. So I'm going to use Copilot to help me get started and actually get these two applications working together. I have a solution, again, with a client and server projects in them. I've got a Blazor API project, which is a web API application, and then a Blazor client that I've used the WASM template to develop. So I'm going to go ahead and open up a terminal so we can interact with these two applications. And I'm going to get started by asking Copilot to generate a C# ASP.NET Core web API controller. And I want it to include all the CRUD operations that I want for my application. Now remember, CRUD stands for create, read, update, and delete. And I want to make sure that my API includes all of those operations so that our Blazor application can interact with it. So I'm going to go to Copilot, and without giving it any context for my app just yet, I'm just going to ask it to provide that type of controller. I'm giving it a specific name. I want it called product controller. And then I tell it what I want that controller to do. Because our application is so simple at this point, this is enough to get started. And because Copilot knows it needs to be written in C#, that it's an ASP.NET Core Web API, and what operations I want, it's going to have enough information to provide me with that basic code. So the first thing it's done is given me a model that I can use in my application called product. And I want to create a controller named product controller with that model in it. And then it's given me the product controller itself, and that's all the code that I need to do those operations. As I create this, I want to make sure that I'm putting this stuff in the right place, and I'm not quite sure where this goes. So it's given me an API controller named product controller with a product model, but I'm not quite sure where I need to put these, and it doesn't really tell me. I'm going to ask Copilot to provide a little bit more information. A very simple prompt. Where do I put the files? It now gives me specific instructions. It says create a folder named models, add a new class named product.cs, and then put that class file there, and it does the same for the product controller. So let's go back to the application. I'm going to make sure that I have a models and a controller folder in this Blazor API project, and I don't, so I'm going to add both. I'm going to add a models controller first. I want to make sure I'm putting that at the root, and then I'm going to create a controllers folder. You'll notice that Visual Studio Code puts the folder wherever you have the cursor, so I want to make sure I'm putting these at the root. All right, so I've got a models folder and a controllers folder, and I'll go back to Microsoft Copilot, and now I can copy these files out and paste them into each of the individual files. So I'm going to create a product.cs file first in the models folder, and I'm going to paste that code in. Now we've got our product class that we can use in our application. I'm going to go back to Copilot, and it's asking me to create a product controller.cs file. So I'll copy this out, create a new product controller CS file, and then I'll paste that code into that file. Now we have both of our CS files created. We've got a product object that we can use and a product controller class that we can call. You'll notice that in here, we're creating a list of the product objects. So there's going to be multiple products, and we want to hold that in a list. And you notice that it detected the product object just fine because this is all part of the same application. If we had not created that product object first, then we would have gotten an error in our code, and we would have had to make sure that we had that created. Okay, we've got the start of our application. We've got our CRUD operations ready to go. And now we can start working on the front end. So I'm going to switch over to my Blazor client application, open up the pages folder. I know that I want to create a page that will be able to call each of those CRUD operations. So I'm going to prompt Copilot now. It's got a little bit of context for our application. So I'm going to prompt it to create a page that I can use to call those CRUD operations. So I'll go ahead and prompt Copilot, generate a WebAssembly component named productlist.razor, and it fetches data from the API using the HttpClient. The component should display products in an unordered list showing their name and price. Now let's make sure that our product controller has all of those items, and it does have name and it does have price. We're in good shape so far. We've got our object that has those two fields, and now we can prompt Copilot to generate that file for us. Here's a WebAssembly component named productlist.razor that fetches the HTTP client, and it's giving that information back to us. It's telling us some things that we need to make sure we change. We have to change the endpoint to reach our server. The product class is used to deserialize the JSON data, and then the oninitialized sync lifecycle overrides the fetch product from the API. There's one other thing it's telling us to do, and that is in program.cs to make sure that we have that client registered as a scoped item in our setup. So we'll have to go back to program.cs and make sure that's there as well. The first thing I'm going to do though is create our productlist.razor file. So I'll go to my application. I'm in the pages folder, and I'll create a new file called productlist and razor, and then I can paste that code. We've got our product list page, so we're ready to use that in our application. I'm going to go back to Copilot and make sure that I get that line of code that I need so that I can use the HTTP client. Now, notice I'm only taking this one line out because I don't want to paste the whole thing, and I think everything else that's in my program.cs file is going to be fine. So I only want to make sure that I have HTTP client that I'm using in that program.cs file. So I'll go back to my client, open up program.cs, and I'm going to add that line. Notice, however, when I got here, that line was already added. The add scoped HTTP client already was a part of the template, so I don't need to add it. So we're ready to go with our application. We can launch both of them, and we can see if it works, if we can talk to the server using the client. I'm going to move to the client folder here in the terminal. All right, so now we've got our Blazor client. I'm going to add a new terminal and move to Blazor API. All right, so now I've got this prompt we can use to work with Blazor API, and then this prompt we can use to work with Blazor client. I'm going to start the project in the API first, and I like to build it just to make sure that there's no issues. And if there's no issues, then we can go ahead and run it. All right, so there's no issues. There's a warning which we can ignore for the time being. but it will run. So I'm going to run this application, the server. And notice that it's telling me that it's running on HTTP localhost port number 510. So I'm going to copy that out because we're going to need that for our client application. I'm going to go back into product list.razor, and I'm going to paste in the location of where that API is actually running from. I'm going to ask it to get a list of products on localhost port number 510 at the route API and product. So that way we can make sure that we're actually talking to the server when we run our client application. So now I'm going to switch to the terminal that is our client application here, and I'm going to build that. All right, that seems to have built fine with some warnings, but we can address those later. And for right now, I'm going to run the application. Okay, so now we have our application running. We've got our API running. And so I'm going to go to the Blazor application, the client application, and it'll open up the browser. And remember, we have our product list at the route product list. So we need to browse to that location. And then it will open up the product list page, and it's retrieved the information from the API. And there's two products. If you'll recall, in our API, there's a $10 item for product 1 and a $20 item called product 2. And it's retrieved that information from the API and populated our Blazor page with it. Using Copilot, we're able to actually build two parts of a client-server application. This is obviously very simple and it's just framed out, but it gives us a start for building on this. We use Copilot to essentially develop the whole thing. Copilot can be a very useful tool, particularly for getting past the initial architecture of an application, client-server application, and making sure that everything lines up and they can talk to each other.
Congratulations on completing full stack integration, part of the Microsoft Full Stack Development Professional Certificate. Throughout this course, you developed essential skills for bridging the gap between front-end and back-end development, enabling you to build fully integrated, responsive applications. From mastering API consumption in Blazor to leveraging AI tools like Microsoft Copilot, you are now prepared to tackle real-world integration challenges with confidence and efficiency. You began by exploring the architecture and components of full-stack systems, getting a solid foundation for connecting front-end and back-end seamlessly. By setting up a development environment, creating RESTful APIs, and integrating them with front-end applications, you built the essential groundwork for full-stack integration. Next, you dove into interacting with APIs in Blazor applications, learning to manage data flow effectively through asynchronous programming and best practices for API calls. These skills ensure your applications remain robust, efficient, and capable of handling complex integrations. Then you mastered techniques for managing state on both the client and the server side. You explored strategies for real-time communication and scalable solutions, enhancing the responsiveness and maintainability of your full-stack systems. Finally, you harnessed the power of Microsoft Copilot to simplify integration tasks. From writing and debugging integration code to creating and optimizing JSON structures for APIs, you applied AI-driven tools to streamline your development workflow. The Capstone project brought together all the concepts you've learned, showcasing your ability to build fully integrated solutions. Having completed this course, you are now equipped with the knowledge and skills to create cohesive, full-stack applications that integrate seamlessly. Your ability to connect front-end and back-end components, manage state effectively, and leverage AI tools for optimization positions you for success in the dynamic world of full-stack development. Congratulations on your achievements, and best of luck as you continue your journey as a Microsoft full-stack developer.